Hopefully you guys see me. Wow. Anyway, hi. I've been looking at the chat as I'm trying to get some stuff up. Hopefully you guys hear me. Let me know if you hear me in the chat. Let me know if you see me in the chat and everything's good. I'm still wiping the sweat off my brow today. At 9:45 my time-ish, give or take an ish, my Spectrum internet, which has been very spotty over the past week, went out. I mean out like a light, like TKO, 10th round kind of, oh my, George Foreman just, did a number on me out. I mean, it's gone. So I had to switch very quickly. And I noticed someone was saying, wait, you have a backup? I think, Chris, you were saying, hey, you have a backup internet? Like, yeah, of course I do, because Spectrum is so reliable that it's given me such a vote of confidence that I never feel I have to get anything other than a backup. So yes, we have a backup provider for exactly this kind of thing. So I use T-Mobile, and it's a backup. It's not, my primary. So if the streaming seems a little strange, if I, kind of get buffering or anything like that, sorry about that. This is my backup because Spectrum is completely out. Good. It looks like you guys can see me and hear me. Wonderful. Everything's okay. Video and audio good. Good. Oh, woof. I tell you, you never, when you have to be the talent, the one in front of the camera and the one behind the camera, and you have stuff like this happen, it's, my mind is trying to think, okay, I've got my mind on all the stuff I want to teach today. And now this other thing begins to spiral downhill. So it becomes this real, like, fight not to panic, just to completely throw your hands up in the air and just, lose it. So I do have my phone with me. So if things go wrong, hopefully Jerry or Keith, I see and Chris, you guys are all in there, and Mike hopefully is in there. All of you guys, if you need to, call me, because I do have my phone with me, and I do think I have it on ring. And for those of you, and I see, is it Andy's birthday? Really? I see congrats to Keith or to Chris. Congrats for something. So someone has to catch me up. Otherwise, I'll have to read the chat, because I see somebody's birthday. Now people are congratulating Chris. And I would love to know what that's all about. Yes, I think I do have the ringtone up, so I should be able to hear. Okay, guys. Hello. For those of you who have looked at, oh, good, Mike, I'm glad you're here. Thank you. For those of you who had looked at my YouTube feed recently, you might notice there's been a little bit of a change in the way I'm showing the mini courses. I have been getting a lot of people asking me over the course of time, which, oh my gosh, Tamitha, you have all these mini courses. That's great, but where, it's just too many. What do I do? Where do I go? Where do I start? So, Andy, oh, it's your birthday. Oh, happy birthday, Andy. Thank you for joining me on your birthday. I would think you'd be out gallivanting around, but instead you're holed up watching a mini course with me with my mason jar. I should get you a mason jar for your birthday. At any rate, happy birthday. So I went ahead and I redid all the mini courses, and I put them in series now. So if you go to the YouTube website, and that's why you might notice the title of this, if you look on the YouTube title, you'll see now this course is called M2. Okay, I'm keeping the names very simple. But the reason why it's M is for Magnetization. That's the code. There, I can tell you what all the codes are very quickly. And I've kept them the way they are because I want to avoid having any courses named the same thing as the Space Weather Prediction Center G, S, and R scales. I'm avoiding those letters altogether because I don't want anybody to associate those scales with any of these courses, because it will do you a disservice. So at any rate, if you look in the YouTube channel, you will see there are all these series now, and each series is named something, and each series has a description. And in that description, I talk about not only what the series is about. So like coronal mass ejections has its own, which are also called solar storms. Radiation storms have their own. Solar flares and radio bursts have their own. So each one of these has their own series. This second chef, as we start going into the different regimes in the second chef, this has its own, and there will be 2 other regimes that you will see come up. So there'll be 2 other series. And each of them have their own letter, and then there are course numbers in there. So it's usually typically, I think the biggest number I have in there is 4. So there's 4 courses in one of them, and I think it's the radiation storm one. And then in the description, you will also see prerequisites, right? So if you start with coronal mass ejections, there's no prerequisites. And then if you go to solar flares and radiation storm, or solar flares and radio bursts, you will see that there are 3 prerequisites, and those are the coronal mass ejection series. So, and I just keep labeling that, so you kind of can, it feels a little bit more like a course catalog and gives you a better feel for where do I go, how do I start, what do I need to jump into, and what do I need to know in order to take this course. So hopefully that will kind of answer the mail when it comes to this, and I'd love your feedback on it, especially my Patreon folks, all the mini course patrons that I'll talk about in a second, because this should help you. Okay. So hello everybody, and let's see. Yes, again, oh good, people are drinking wine. I have to drink water. Otherwise I will not be a very good teacher. But so again, these are all my mini course patrons. Let me, oops, I got to stand on the right side. My view of course is mirrored, so I've got to be careful there. I always go the wrong way. I have to say a big thank you to my VIP steering committee. You will see a few new names. We can welcome Blair, for example. He's a new one. And I just had a really nice meeting with Blair. He's going to make me work, I tell you, for being on. He's got a lot of questions I have to answer, and I really appreciate the VIPs because they really help steer the ship. They help determine really where this space weather community is going, where we need to fill in gaps in people's understanding and knowledge, where we need to draw the different communities together, and really what makes this, they're the heart of this community, there's no doubt. So I get together with them once a month, and we talk shop. We talk about what's going on, how we're working it out. They right now are getting sneak peeks at some of the educational work I'm doing with the ARRL right now with Nathaniel Frizzell, which is a lot of fun, and they get to help me build out some of the content. It's really great, and they give me incredible insight. So I'm very grateful to all of them. And then also the mini course patrons. Here are all the wonderful people who make these courses possible. And I wouldn't, I just bow to you all because you've helped create the flow, the energy of this community. And I'm so grateful. And some of you have been with me for years now, and I love you to death. So be sure to ask questions either in the chat or ask questions on Patreon. I am looking at both. I probably won't look at Facebook, but I'll try if I remember to, because I have had a couple of people ask me questions there. But definitely I will address questions today. And this will not be the end-all be-all of the second chef. So I have had people ask me questions that are kind of really leading us down the path of some of the other regimes that are going to be coming up here in the next, oh my goodness, probably 2 or 3 months. We can't answer all of the questions today. Just because I'm going into current systems today does not mean we will get to all the current systems and how they affect people on the ground. But you will see that as time goes on. And any questions about and I'm not going to do a lot of review because we're kind of going to do a review as we go on, but any questions really quickly before we begin? Any like dying, burning questions from anyone? I'll take just a second as I load up. Where do I want to start here? This is the same part of the talk as before. So I have all the same charts as before. We did not get very far last time, which I think was super important because I think everybody remembers L shells, right? Let me go to this chart. This is what we really had to sit down and really focus on last time. And the reason for that is because if you don't understand this concept, you'll be lost in terms of understanding anything else, because it actually gets a bit more complicated from here on out. This was actually very savvy of magnetospheric physicists early on to figure out how to do this and why. Because early on, right? I mean, space weather has been affecting the Earth and the people on it since long before we had satellites, right? So there was a many, years, decades that we knew about space weather, but we couldn't probe it necessarily. And a really good example of that is World War II, right? At least in the United States, HF propagation, right? And just anywhere in the world. The radio communicators, they knew that the upper atmosphere was being bombarded by stuff from the sun, but we didn't have satellites up. We couldn't really probe directly what was going on. So we had to kind of understand space weather from mud first, right? We had to understand it from the ground up. And as we had models of the Earth's magnetic shield, we began to understand how that shield ordered things and how it made certain things on the ground happen in certain places, right? And so they came up with this kind of depiction of the Earth's magnetic field, and we came up with the depiction of L shells and how they mapped to the ground, right? And that you have higher latitudes have higher L shells, lower latitudes have lower L shells. And that makes a huge difference in terms of, as we learned last time, it makes a huge difference in terms of how much activity you see and what has to hit the Earth in terms of space weather for the level of activity that you see. And we learned last time that the L shells out on the outside, right, the ones that are further out, they see more activity. Remember the model? And I don't have that movie up. I probably should have pulled that movie up, but I don't have it right now. Of last time we had the magnetosphere, and you had that solar wind slamming into the Earth's magnetosphere in that particular model, and you saw not only were these L shells kind of springy, right? They'd bounce, but you'd also see them being pulled in the flux, being pulled back and pulled away, and then it would reform, and then it would be pulled back again, and it would fold over into the Earth's magnetic tail, right? And I shouldn't be doing it with this diagram because it's not a great diagram for it, but if you recall all that dynamic, right, is far more crazy and almost chaotic at higher L shells, the further out you go. But the heart of the Earth's magnetosphere, right, down in the low L shells, is pretty quiet, right? It's harder to get to. And it's harder to get to by a lot of different phenomena, not just the solar wind slamming in, but also radiation storms. When they slam in, they have a hard time getting to the heart because this magnetic shield shields them out. And even galactic cosmic rays are shielded out to a great degree, especially down at the heart. So really, where a lot of the action that happens at these high L shells out here, right, they map to high latitudes up here, right? They map to these high latitudes. So that's why you get so much stuff, as we'll see as we look into some of the data products that the Space Weather Prediction Center creates for us. Why, for instance, radiation storms end up penetrating so dramatically, both at high northern latitudes and high southern latitudes, because that's where the holes are. It's where a magnetic shield just doesn't shield. It's open to the solar wind, and stuff comes in. But you've also seen, as we saw last time, from the tail, you'd get the slingshot effect, where that you'd stretch out the tail magnetic field and it would come back and slingshot. So hopefully everybody remembers that. Nick, you're funny. Yeah. Thank you. No, I saw your message, so it's fine. Oh, good. Hey, Deepak, good to see you. We have people from India here, from Jakarta here. Okay. Yes, finally get it. Good. I'm so glad, Keith. And can I just say I've learned so much more listening to you and parsnips onto my weather. What? Jim, and parsnips, is that what you meant to say, that onto my weather team in the US? Correlation between L shells, D, E, and F layers. Yes and no. And it's good that you say that, and we will get into that specifically. The concept of D, for those who are uninitiated, the concept of D, E, and F layers, these are layers of the ionosphere, and we will get into that far more in what I call regime 2, that will be labeled the I series of courses. Because we have to kind of peel, just like we peeled the sun a little bit like an onion, we have to do the same thing with the Earth's magnetic system. So we start out at the edge, basically where the Earth's magnetic system starts, right at the bow shock, like we talked last time. and we peel it down. And as we go down and through the magnetosphere, then we get really close to the Earth. Whoops, I went too far. And then we get to the Earth's upper atmosphere, which is the ionosphere. That's where we're going to find those layers, and we'll talk about those layers. So yes and no, in the sense that the ionosphere is, because it's charged, it's going to see the Earth's magnetic shield, and so it's going to be shaped by it. And because of that, the ionosphere actually tilts a little bit because the Earth's magnetic field is tilted. But the ionosphere is not nearly as dominated by this region, by the Earth's magnetic system, as the outer part of the Earth's magnetic system is. And the reason for that is because we actually have what I call, I kind of call it a waterbed. It's the neutral atmosphere waterbed. I know that seems strange. Wait, atmosphere is air. Why is it water? No, it's the reason why I call it a waterbed is because it's this contained fluid that if you're sitting on the top of it like a waterbed, it wiggles and waves and it makes you go blah, 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 right? You're on top of it, kind of bouncing around. And that's kind of what the ionosphere does, sitting on top of the neutral atmosphere. It's not this pristine, completely oblivious, I'm here and I don't feel anything. No, it feels the waves being generated in this waterbed underneath it. And so it's sitting on top of this surface that's undulating. And so the ionosphere is very dynamic, both because it's sensing all of the magnetic field stuff coming from above and all through it, right? Because the Earth's magnetic field comes from the core of the Earth. So it senses all of this magnetic field stuff and has to obey, because these are charged particles, so they see electric and magnetic fields. But it also is sitting on top of this waterbed, on the surface of this neutral atmosphere waterbed. And the waterbed feels forces just from the Earth spinning round, right? It's the type of neutral atmosphere dynamics that we learn in terrestrial meteorology. So the ionosphere is extremely complicated, and we will get into, to some degree, in the ionosphere regime, we'll get into that a bit more. So when we start talking about D, E, and F layers, we're talking about a very, very, let me go over here, small section, like maybe like this, right out here. So we're talking about like this tiny layer here. I mean, not even that high, right? So we're talking about L shells maybe out to 1.5 from that perspective. And so it's not really the same, right? Plus the layers on the ionosphere really matter whether it's day or night. Earth's magnetic shield is there all the time. So, you can see really quickly how that trying to correlate the two breaks down really fast, right? Because the Earth's magnetic shield doesn't care if it's daytime or nighttime. It cares if there's solar wind hitting it, and it elongates the tail, but it doesn't really care about what the sun's irradiance is, if that makes sense. So we have to be a little bit careful. We have to understand that the ionosphere, yes, it does matter. The Earth's magnetic field does matter, but it's definitely not the whole story. And to make those correlations can be very dangerous. That's really advanced stuff, and you have to know where the limitations are. So hopefully that answered that question. Yes, we're peeling the onion. So let me stand. Remember the regimes here, right? The main regimes. Now there's a lot more than this, but we have the ring current, the plasma sphere, and the radiation belts, right? Oftentimes called the Van Allen belts. And yes, there are two of them, and we will talk about them more today. The reason why I bring these main things up is to let you know that, number one, they're co-located. So if you look here, you can see both. Here's the radiation belts, both the inner zone and the outer zone, inner radiation belt, outer radiation belt. But you also have kind of co-located, especially with the inner zone, you have co-located with that the plasma sphere, which is the blue, which you can barely see, and the ring current, which is the purple. Or excuse me, the blue is the ring current, and then the purple is the plasma sphere, and they're kind of co-located. And the ring current even comes out, if you can see some of this blue out here, it even comes out really to the edge of the Van Allen belt. So there's current systems, because all of these have their own kind of current systems. All of these are, are all in and through the whole regime of these L shells. Okay, there's really no space that there's nothing. So if anyone who's ever heard about flying in the slot, or we can just stick satellites in the slot, that doesn't really exist. It's a nice anecdotal, not anecdotal, but academic kind of concept, but it doesn't really bear out in real life because there's just a lot of smearing of stuff. We talked about that last time. So now we're going to start getting into the real current systems. Okay. Now I did talk about this last time, but again, why we're going to get into this in more detail today is because we're actually talking specifically now about how these different current systems begin to map down into the Earth's upper atmosphere, down into the ground eventually, and also where they are located in the Earth's magnetic system and why. Okay. And then how, of course, these types of things, these different regimes end up, or regions rather, end up impacting things like satellites, okay, in our narrow system. So as I talked about last time, here's the solar wind, right, blowing into the system, okay? And yes, we have a magnetopause current. So at the front end of our Earth's magnetic shield, we have a current that moves to dusk. Okay, if the sun is coming in this way, dusk is this way, dawn is on the other side. Okay, hopefully that was clear from last time. And so this is on the edge of essentially the edge of our magnetic system is the magnetopause current. And there's a magnetopause current that basically goes all the way around the whole edge of this magnetosphere. So in fact, you see this tail current up here. See this tail current up here? This is actually the closing of the magnetopause current. Okay, and at the equator, it goes up over the top, comes down. I'll show you some different pictures. Goes across in the middle. Whoops. Let's see. No, I need to move this way. Give me a second to get reoriented here. So hopefully you can see this yellow line. If I can get the yellow arrow, it's not very easy to see, but this current goes across this way, and it goes up around the edge here, and then goes down the other side, and then comes back. That's what it does in the northern hemisphere, and in the southern hemisphere, it goes down that way. And we'll talk about that more. But that's the magnetopause current. So it's basically running on the outside of the Earth's magnetic system, which, as you know, looks a little bit like a comet tail, right? Especially as the tail stretches out. Okay. And as we also talked about it, this system, let me kind of stand on this side for now. This might be a little bit easier. I talked about it last time being a cut. So we're cutting right through the from north to south, right through half of the Earth. Here's Earth over here, right? You see this little globe. We're cutting through it, and then we're turning the knife sideways, and then we're cutting straight out this way. So this is like a pie slice. And so you're looking at the equatorial plane, essentially, right? And here you're looking at the north-south part of it, the meridional or meridional cut, depending upon your pronunciation of the word. You can see the cusp right in here somewhere, right there. There's the cusp going straight down, so particles can get in here at the cusp. And you notice the current systems. We're starting to see all these colors, these current systems. Now, sharing the outside, or nearly the outside of this system, is one in particular. Notice this blue line that comes out of what looks like the very tippy top of the Earth's North Pole. In other words, very high L shell. And it maps all the way to essentially the outer edge of the Earth's magnetic system. Okay, this is a field-aligned current. So in other words, part of the energy that is coming in from the solar wind, and also just the interaction of the solar wind at the very highest latitudes, some of that is being coupled in to current systems, okay, near the edge of the Earth's magnetosphere. Okay, these both field-aligned, both region 1, which is the one that's on the further outside, and then region 2, which is a little bit further in, right, the red line. So you can see it's a little bit inward. Okay. These are current systems that are coupling in to the Earth's polar region. And we will zoom in on these a lot more in regime 2 when we start talking about the ionosphere. But suffice to say, I've heard more than one magnetospheric physicist call the polar cap, the polar region of the Earth, basically they call it the Earth's magnetic field's exhaust pipe. And the reason why is because a lot of the energy that we have that's from space weather, right? That's coupling into the Earth system from solar wind interaction ends up being pumped down through these current systems right into the Earth's upper atmosphere. And what happens is when those currents get pumped down to the Earth's upper atmosphere, they dissipate. They get pushed through this upper atmosphere, and they create heat, joule heating, which we call it, and dissipation, and it lights up the Earth's ionosphere, right? You get aurora. And that is actually how the magnetic system, this whole magnetic system, lets off steam. It blows off the energy that way by pumping it down and letting it just kind of, fizzle itself out, burn itself out, so to speak. So that is the function of, well, it's one of the functions of the field-aligned current system. Okay, so you go in with region 2, at least on this side, in region 2 on this side, into the Earth's upper atmosphere. It moves in a little bit and then it pops back out. Okay, in region 1. And the other side, it's the other way. And we'll talk about that. We'll revisit that more later. Okay, but just suffice to say that is one of the highest latitude current systems that we have. And it's a very, very big current system. People get entire PhDs studying just region 1 and region 2 currents. It's unbelievable how dynamic, because you get into Hall currents, you get Pedersen currents, there's all sorts of dynamics that go on that is way beyond the scope of this. And get a PhD if you're interested. But it's very, very complicated stuff. But the interesting thing that you need to know is that because it's very close to the edge of the Earth's magnetosphere, right? You're going to be seeing these effects at high latitude, right? So if you ever wonder why aurora happens at high latitude and not low latitude, well, with the way the Earth's magnetic system is built, this is why. Because you get stuff happening at the very edge of the Earth's magnetic system. So very high L shell, and therefore that maps down to very high latitude on the Earth's surface. Now, as we move further in, right, you're going to start seeing that ring current. Okay, see that purple, the ring current? Now that ring current is further in. That's like around anywhere between 2, 3, 4, 5 L shell, L of 2, L of 3, L of 4, L of 5. Mostly around 3 to 5, but it depends just a little bit. So it's co-located with basically the outer edge of the inner zone, and it's co-located with basically the inner edge of the outer zone. So being co-located with the radiation belts is, these particles share the same gel cell. It's just that the particles have a slightly different energy, and we'll go into that if we haven't already. But notice the ring current is further in than region 1 and region 2. That should immediately tell you that we are looking at a current system that's going to map to lower L shells, right? And sure enough, it does. When we start looking at indices on the ground, we'll actually be able to pick out which magnetometer stations to look at what latitude, to be able to focus on these different current systems, right? To understand what's going on. Now, the ring current is basically the energy. It's the main energy of the magnetic shield. So when the ring current, it's like kind of like the slow brontosaurus. It's got a lot of inertia in this sense. I shouldn't use the word inertia. That's a bad word because that's a physical word. It's the slow mover in the sense of when you have space weather events, to get the ring current to energize takes a lot of time, takes a lot of sustained energy, takes a lot of persistence. Okay, but when that ring current moves, when that ring current starts getting energized, it's so profound, it has such a profound effect on the whole Earth's magnetic system, is that it actually depresses the strength of the Earth's magnetic field. And we measure that. That's one of the things we measure in our indices. It's called DST, Disturbance Storm Time Index. And we actually measure how much this ring current, by energizing itself, can actually create a magnetic field intensity of the opposite strength and polarity, and it actually depresses when it's added to the magnetic field, that already exists. It actually depresses the strength of the magnetic field overall, and we actually measure that. So anytime you see dips in DST, for those of you who are interested, that is what we're measuring. Okay, but it's at a lower L shell, right? And it's a massive amount of system. And then when we get into the plasmasphere, we'll talk a little bit more about that when we get closer to. Well, I'll talk about it in a little bit when we start talking about wave processes, but I'm not going to talk about a current system associated with that. But that's where we get a lot of particle precipitation into the Earth's upper atmosphere. So already you can see, just with me trying to take a very simplistic view, this gets complicated, and it gets complicated fast, okay? Because there's a lot going on. Here is another way to take a look at it, okay? So now we're looking at the same kind of system, but we're looking at it, hopefully I'm not jerky, okay. Whoops, my door just opened. No, oh, for goodness sake, hold on. Here. Just take them, okay? My daughter, I need batteries, Mom. Okay. Oh yes, don't you love working at home? Okay. So here is the same diagram. Remember, what I always do is I always try to get diagrams that you see the same thing from multiple perspectives, because it helps you internalize things better. So here's the same system drawn in a slightly different way. This is also a very famous paper from a very famous author, Bob McFerrin. Anybody who wants to know anything about substorms, go look this guy up. He's unbelievable, from UCLA. It's also a good friend of mine. And from this system, you're looking at it from the tail, okay, and that's why you see tail current. And excuse me, I'm seeing everything backwards. I really hate YouTube because it mirrors everything, so I have to read over here instead of looking at you guys. It's terrible. But looking at it here, the sun is obviously in the front on this other side here, and you're looking at multiple current systems in a more idealized fashion, right? Because everything's round. So again, if you have from this line here, dawn dusk, oops, let me tilt my hand the right way. There we go. So here's the dawn dusk line. So obviously the sun is in front of you over there. I mean, not in front of you, behind the page. Dawn is going to be on this side. Okay, so the Earth is rotating this way. Okay, I'm going around like this. Dawn is over here, dusk is over there, right? We're looking at the night side of Earth, essentially. Okay. Now, just because you don't see L shells, just because you don't see a magnetic system, doesn't mean it's not still there, right? High L shell means far out, really far out, right? Low L shell means close to Earth, okay? Notice which current systems do you see way out on the edge? Of course, you're going to see the magnetopause current, right? That's the outer edge. That's as high as L of, I don't know, I guess you'd have to call it infinity, because it's right at the very, very outer edge, L highest. Outside of that, it's solar wind or disturbed solar wind. So when you move just inside that, what are you going to find? You're going to find the high latitude current systems, region 1 and region 2, right? So here's region 1, this first green line, and then region 2, just slightly inward, okay? Very, very high L shells. The next one is going to be the ring current. That's the brown, okay? Hopefully you can read the writing, okay? And then things get a little bit more complicated, because now I'm showing you just a little bit how not only how complicated the green system can get, right? Because you see it going in and going out, and then it actually goes across the pole, across the top of this Earth system here, in through, we're getting in through the ionosphere in here. There's actually current systems that go across, and then you can see it going out again and in, right? Hopefully I can, but you notice that, oops, I'm doing it in the mirror again. Notice that the region 1 current system on the outside goes into the Earth on the dawn side. The region 1 current system on the dusk side goes out. See that? So they change direction depending upon if you're on the dawn side or the dusk side. Okay. You also have things like the partial ring current, which is another more subauroral thing that comes down just outside of, typically right around the same as region 2, but just outside of the ring current. See that? That's that dark blue line. And you also have tail current and disruptions in the tail current. We often call this the substorm current wedge. And you can see that also couples into, whoops, my hand goes the wrong way. That also couples into the Earth's upper atmosphere or ionosphere. So current systems, as you begin to look at them, especially all the stuff that's dynamic, that is showing the dynamics of storms, of the upper atmosphere, the high L shell upper atmosphere. you can start seeing that things get complicated fast, because this is an even more complicated diagram than one before, right? Because now we're adding the partial ring current and we're adding the substorm current wedge. Believe it or not, the substorm current wedge is very much related to dipolarization. Remember in the movie in the last course, when I showed that movie and I showed how we have the X line in the tail, right? And things, and we get slingshotted forward. Believe it or not, you don't even have to have a real big geomagnetic storm, a big storm going on. In other words, a big CME or ICME hitting Earth and driving this big massive storm. You can actually have small little things happening, sometimes not even triggered really by what's going on in the solar wind, but just have a configuration in the Earth's magnetic system where it's kind of like loaded. It's kind of already, latent, like stuff that's just been lingering, maybe from a prior storm or something. And the Earth decides, the magnetic shield decides to reconfigure. It gets an X line, gets magnetic field of different directions really close together, causes reconnection, and zip, you get this little slingshot of stuff. When you get those slingshots, those are often called substorms. When you get those slingshots, you get this substorm current wedge forming. They're tail disruptions, right? Because you get currents in the tail. Those currents help to drive those field lines closer and closer together. Anytime you have field lines that are opposite of one another, you have a current in the middle of it. That's why you have this tail current to begin with. So you have fields that are very close together going in opposite directions, and those currents change. And as you can get breaks, get reconnection here, you can get these disruptions that then shoot stuff. Whoops, I do it the wrong way. Shoot stuff from the substorm current wedge all the way into the Earth's magnetic system. Again, far too complex for this class, and far too complex really for any of those who if you want to study this, you definitely would be studying substorms. And Bob McFerrin is just a real powerhouse in that. And perhaps as I get into things more in depth, like after we're done with this series, the Space Weather Basics series, kind of, I can go into some of these advanced topics in more detail. But as we do that, man, it's going to get complicated, and I don't know if I'll be able to do it without really going into the physics. So I mean, with equations and things like that. So it could get that may be very difficult to teach conceptually, because you can see this gets very complicated. And there's all this interplay between the magnetic system and all the currents that are being generated. Right? It's not just about currents. We're not dropping Earth's magnetic system and just now looking at electric fields. No. Because the fact that the currents are there are very much driven by what's happening to that magnetic field and how that magnetic field is interacting with the larger magnetic field of the sun that is, being brought out in the solar wind. So it's this ballet, okay? And it becomes extremely complicated depending upon how you want to look at it. So yeah, for example, this diagram is showing the magnetic field lines. Okay, this is not a current system. This is just, it looks like spaghetti, I know, but all the red is showing open field lines. Okay, so here is Earth, and if you look at the X direction, that is toward the sun. Okay, you can see that. That is toward the sun. That's the Earth-Sun line, essentially. Y, if you see where the Y is pointing, that is the dusk direction. The opposite, negative Y, the opposite is dawn. Okay, so hopefully that lets you see. Remember we were talking about flux opening? So here, this magnetic field line coming down, this red line right here, coming down at the beginning. See how it's opening up the flux? That's solar wind opening up, just reconnecting with the Earth's magnetic system and opening one of those L shells. Okay, now remember, these are shells, not we're showing them as lines to be simple, as if this were simple. But it's really a big shell that's being peeled open, right? It's a layer of that onion. And so they're just showing it opening up, and that's going to be folded back and put into the tail, okay? Remember, at the poles, we have all those open field lines, and that's how that happens. It always happens at high L shells. So as you can see, that hole with all those open field lines gets bigger depending upon how much of that onion you're peeling back, right? This is why that whole area in the upper atmosphere is so dynamic, and I'll show you that here in a sec. You'll see, look at all that stuff back there. That's all happening in the auroral cap, okay? This is the reason why it's so dynamic and why there's so many current systems going on all at once, okay? Is because there's all this flux that's constantly being peeled back. Now, of course, the blue lines are showing where the closed field is. Right, you're seeing, right, you can actually even see some of them that look dipolar. Remember, dipolar is what looks like a dipole field. You can actually see the nice round, you know, slinky looking like magnetic field lines. If you squint your eyes, you can see the nice slinky ones. And then, of course, you can also see the ones that look like they've been stretched back like a slingshot, right, that are loaded and ready to snap. Okay, so you're seeing all of that here. But this is just the magnetic field. On top of that, you have your current systems. Here is the magnetopause current system, essentially. Okay, and you can see in the pink, right? So what they've done, all that gray stuff is the field lines. Okay, they've grayed it out now so you can focus on the current systems, right? Because all of this is happening all at the same time, all overlaid on one another. So this is the basically painting, in a sense, the outer shell of the Earth's magnetic system, except of course it has to close in the crosstail current, which is the pink. So hopefully you can see the arrows. This is the crosstail current that goes from dawn to dusk and closes in the northern hemisphere, closes by going around the outside of the Earth's magnetic system back to dawn. And it goes from dawn to dusk in the tail at the equator and goes out, up, and over. In the southern hemisphere, it does the opposite. The crosstail current always points the same way, from dawn to dusk, but then in the southern hemisphere, it flips. It goes from, southward. It goes from dusk back to dawn, the opposite direction. Okay, so you have that current system. And they're even showing a little bit of the current wedge, but don't worry about it. That's just a little too complicated. And then you're seeing region 1 and region 2 currents. And of course, a partial ring current. The partial ring current is in pink. The region 1 currents close at the magnetosphere. So you're seeing, essentially in the magnetopause current. And then region 2 currents are inward of that. And you can even see a partial ring current where it couples, where the region 2 currents, in a sense, couple into the ring current. They don't just couple outside of it. Okay. And it gets nuts. Look at what's going on in here. Okay. You have field-aligned currents, you have auroral electrojets, we have particles that are precipitating in, of course, tons of electric fields, which we just talked about in currents here, right there. And you even have, and they're even showing, you even have neutral processes that help drive, and gravity waves that help drive some of these processes here. You can see this is where the auroral electrojet ends up taking in. When you have aurora, believe it or not, when you get aurora, you actually get heating and currents that are driven down into lower latitudes. And there's coupling into the neutral atmosphere. There's actually convection going on. Now, this whole part of it, we're not going to talk about today. As you can tell, it's very, very complicated. Okay, and so we'll talk to some degree about it when we get into the ionosphere. So just in case you think that, the ionosphere part is going to be boring, it's not. Okay, but this is mainly up here. It's mainly all the action is going on at high latitudes. I don't know if you guys can hear this, but we have coyotes that are going crazy right now, just outside our, and I have the door open. So if I seem distracted, it's because I'm listening to the coyotes going nuts. And then you also have coupling from the auroral region into the day side of the ionosphere. Remember, we talked a little bit about how, and I just mentioned it because of the DE and F, the question about the DE and F layers, how does that couple into, the L shells? Well, it doesn't really, not to the degree that you might think, but there is some talk. And the talk really comes from how the auroral zone and the dynamics of the auroral zone and some of the current systems there are coupling into some of these current systems on the Earth's day side. Okay, and again, this is stuff we'll talk about more when we get to the ionosphere, but more in a conceptual point of view. But anybody who's an amateur radio operator should be able to take a look at this and feel relieved, because this is why we don't understand radio propagation very well. There is so much going on that it makes things extremely fluid and extremely dynamic. And because the Earth is rotating, different locales on the Earth are rotating in and out of this mess all the time, because this is essentially stable. Okay, the current systems don't rotate with Earth. So in other words, you don't have the region 1, region 2 current systems suddenly rotate and they're facing sunward and one's down the Earth's tail. No, these current systems stay they stay where they are. And, they may tilt a little bit with the Earth's magnetic field, but they stay where they are because they're very much driven by the solar wind coming at us. And the solar wind is always coming at the day side of Earth, right? And so it sets up current systems that are stable, that stay on the day side of Earth, and sets up current systems that are stable, that have the Earth's magnetic field shooting down tail. So the Earth's magnetic field, it rotates with the Earth, but the dynamics is essentially stable. Okay, so you have systems that are rotating and systems that aren't rotating at the same time. See how complicated this gets? It's complicated. If anybody confused? Oh, good, Jerry. I'm glad to see you. I know you had the nets. I'm glad to see you here, though. It matters if the sun hits solar maximum. Yes, all of this changes a little bit depending upon what the dynamics of the solar wind are doing. So, this obviously the essentials stay the same of these systems. So when you're looking at the way the Earth's magnetic field is, it stays essentially the same. You're looking at the way the current systems are set up, they stay essentially the same. Of course, depending upon what space weather hits Earth, you're going to get intensifications because, obviously if a big ICME is hitting Earth and it's dumping a bunch of energy into the system, you're going to get a huge intensification in auroral current systems. But there's even region 1 and region 2 currents, even when this stuff is switched off, right? They just change a little bit because of the configuration, because you're not getting nearly the peeling back of the onion, right, in the Earth's magnetic field system, because there's not a lot of energy going. Let's say this field, instead of the solar wind field, instead of being north or southward, is northward, right? And so you're not peeling this flux back, so you're not introducing all this energy in the tail, and you're not causing all the dynamics that we talked about last time. So these systems will be weaker, especially auroral systems, and they may shift a little bit. Okay, we get theta aurora and other types of things that we'll talk about later, but the essentials are the same. Okay, so oh good, Mike, I'm glad you guys couldn't hear the coyotes. I sure did. They're quiet now, thank goodness. But this is hopelessly complicated and I love it. Okay, I'm glad you love it, because I'm sitting here thinking how many people are like switching off, right? It's like click, I'm done. Is space weather contributing to an uptick in earthquakes and volcanoes? Oh my goodness, that is such a loaded question. And the sad thing is there coupling? Possibly, but mainstream science is hopelessly lost in trying to understand just the primary drivers of this stuff, to then say, well, is that actually affecting tectonics and conductivity on the ground? Is the conductivity and the currents being driven into the ground, which do exist, right? We do have GICs and that type of thing. Is that affecting earthquakes? Is that causing volcanoes? Wow. How do we quantify that? If so, how much? We really don't know yet. And I think it's going to be decades before we're able to reliably even dig into that. Simply because, first of all, geophysicists, they don't even understand the primary driver of earthquakes and how the forcing occurs, right? This is why we can't predict earthquakes to any relevant degree. And earthquakes, because there's so many of them all the time, they correlate with everything. I mean, I literally could sneeze right now and find an earthquake that happened at exactly the same time. And therefore, my sneeze caused that earthquake, right? And it's like, no, you can't do that. You can't do that. So you can correlate earthquakes and not necessarily volcano eruptions, but earthquakes definitely, with pretty much anything you want to. And that's part of the problem. And then when you soften that into soften it away from even needing to predicate the existence of an earthquake, but rather say, well, the earthquake that was already going to happen is more intense. That's even harder, because that even softens the blow more and makes correlations even easier. So the problem isn't correlating earthquakes, let's say, with space weather events. It's the causality, right? That's where mainstream science puts their hands up and says, well, I'm not going to touch that, because there's so many arguments as to why it could and why it couldn't, that I think mainstream science is completely, they just don't even know where to start. They're just because it really does fall into the realm of speculation. Now, are there reasons why there would be effects? Well, sure. There's also reasons why there'd be tidal effects, right? Why the moon should be causing earthquakes, because there's tidal forcings, right? There's planetary forcings. There's all sorts of forcings everywhere. The question is, are those forcings strong enough to drive, an actual, realizable, mechanistic change? And that's where mainstream science just goes, we can't answer that question, because we look to the geophysicists, and the geophysicists say, we have no idea. So I hate to say it, but I think that question is going to be lingering for a much longer time. I think where we're going to be able to make more headway, to be honest, is understanding the connection and possibility of intensification of things like hurricanes, intensification of lightning, intensification of terrestrial weather in the neutral atmosphere, terrestrial weather effects that are related to space weather. I think once we make that connection and have some quantitative studies that don't fall into speculation, that don't fall into a fringe science regime. Once we get to that point, I think then there will be more and more people who will look at the idea of space weather connected to terrestrial events on the ground. There'll be a bigger chance of that. And I think where that's going to manifest will be in geomagnetically induced currents, because really you set up these potential differences in the ground. It doesn't take a physicist very long to say, okay, well, if the bedrock here has one conductivity, bedrock here has a different conductivity, and then you have a big geomagnetic storm happening, there might be electric fields and things set up there that actually could end up being, forcing. So it doesn't take, a wizard to see that there could be connections there. But it's just the quantifying, the ability to quantify them that becomes difficult. And I think we're going to have to follow that path through atmospheric weather and how that stuff couples down before we get into the more complicated stuff. As if this isn't complicated enough as it is. See why there's so much low-hanging fruit already just in this, that space weather physicists say, I'm not even going to bother with the neutral atmosphere, and then even coupling stuff to the ground and just, other areas. We don't even understand how space weather works at Earth yet very well. So hopefully that answers that question, probably a bit more intense than you'd like. JD, please don't sneeze. Yes, I'll stop, I promise. No more earthquakes, I promise. Is CERN possibly affecting these energies? Yeah, probably not. What's going on inside those magnetic fields is local, and I mean that really starts getting into a whole nother area that I have not studied. Are there effects at all? Well, I don't know, maybe locally, but how far-reaching are they? That's a really crazy question. And I think people who know CERN, that reactor, and who are magnetotelluric assayists may understand that, may have more insight into a question like that than I would. But that's an very interesting question. Could there be some local things? I don't know, and I don't know how much they shield the magnetic field in those big, in the big containment, tunnels that they've created. So I know humans walk around and they probably aren't getting magnetized. Hopefully they walk around and their necklaces aren't like zing. Every time they get near something, it's just like pulling on them. I know people who work near transformers, big electric transformers, and they've actually had that. They've told me about their necklaces. They can feel them tugging. And it's like, oh my Lord, I do not want to be anywhere near a transformer that big. So I would imagine I'd have the same kind of deference and reverence for something like CERN if I were to get near it. Not something I'd be super excited about. So, okay, hopefully that, I know that isn't much of an answer, but yeah, that's the best I can do for now. And okay, all right, I can't answer all these questions, guys, because some of these questions are, we're talking about the Earth's magnetic core, and now we're going to talk about, how does the Earth's magnetic dynamo get created? That is a different course. So I will have to, it's not that I'm trying to ignore these questions. It's just that I can't take the time to talk about that stuff because we're going to get way too far sidetracked from here. But I will do a course on the Earth's dynamo. It's really fascinating. So it's a lot of fun. And I can talk a little bit about our place relative to Venus and relative to Mars, how Venus is our past and Mars is likely our future. Not in our lifetimes, obviously, but in Earth's lifetime. So There are so many sensitive people who need to follow space weather to avoid adverse reactions. It is important. I love your show. It's outstanding. Thank you. And yes, I come across more and more of these people every day. As a matter of fact, one of them, Lourdes, is one of my VIPs, and I love her to death. And she is of that sensitive class. So we are working, and I've been talking to a few other people about some of this work, being the sensitivity of electric and magnetic fields, and how that plays into our body chemistry, and some medical, some reputable medical studies that are being done that are no longer just like speculative. They're actually using real statistical analyses, using credible sources, and knowing enough about space weather to actually make good decisions when it comes to looking at particular phenomena, instead of just trying to lump it all together and not making any sense of it. So we're getting there. We're getting there. But yes, there are people who are sensitive as well, and obviously animals too. Okay. Does mining of different metals impact or shape the magnetic field lines? Locally, yes. As a matter of fact, a perfect example of that is actually off this planet. When we go to Mars, Mars is a remnant magnetic field, believe it or not. It used to have a magnetic dynamo, but it died. The dynamo quit. And yet, as we even fly around the planet, we can measure the magnetic field that's still there. And what that magnetic field is, we call it a remnant magnetic field. And the reason why it's there is because the rocks and the minerals in the rocks, the little magnetic dipoles inside the metal, actually got magnetized. Just like you can magnetize certain metals by putting up them and rubbing them against different metals, or putting them next to magnets. You can magnetize, and you pull away the magnet, and suddenly you have a magnetized piece of iron core or whatever. It's the same kind of process. So that's how we actually knew Mars early on had at one point had its own magnetic dynamo, because the rocks are magnetized in a particular way. And that really does, for Mars, it really does impact what kind of dynamics go on with the solar wind. As a matter of fact, at Mars, you see Aurora in ultraviolet because of those remnant magnetic fields. It's a totally different system, but it's all due to that. So yes, is there magnetization of the rocks here at Earth? Absolutely. Absolutely there is. Does that affect the Earth's magnetic field in general? Yeah, not really. I mean, it's the Earth's magnetic field that did this to them. So they're just aligned in where the Earth is. And it's a lot, it's a lot weaker, right? So we really couldn't measure it unless we're really, really looking at, high, very, very high sensitivity, and looking at really weak magnetic fields. So, not really going to impact us in terms of space weather. So, okay, let's see. I'm familiar with the effect of large ships going through water and disguising systems, so that makes sense. Removing significant amounts of metal from a geographic location would change things. Yeah, it could. Yeah, and a matter of fact, with large ships, we had, that's how back in World War II, and even a little bit later than that, in the 60s and 70s, how we had mines. We actually had sea mines that would be triggered by metal hulls going, driving by, or boating by. And because they'd notice these magnetic relays would notice a change in the magnetic field, and it would trigger the relay to go off, and that would light the bomb up. We've had, in fact, in the geomagnetic storm of 1972, that was classified for quite some time, right? We had like 4,000 sea mines go up because of a big geomagnetic storm. A big Carrington event hit Earth, and it lit up the entire minefield. I think I talked about that in one of my other courses. I have to remember which course that is, but I think it was when I was talking about coronal mass ejections, or interplanetary coronal mass ejections and Carrington events. I think I went over that. So it's one of the C courses. Yeah, one of the C courses, like C3 or C2, something like that. See, I now can reference the name of the course. That's pretty cool, with a number. Okay, so, oh, good, Horatio, thank you for coming in from Argentina. Wonderful, it was so great to have you. Do dental and metal implants make someone more sensitive to EMF? Maybe your teeth. Yes, but medical implants do, absolutely. I've had people who have metal plates, and they're part of that sensitive group. They have metal plates in their skulls, and when a geomagnetic storm hits, they have migraine headaches, or their bones ache. If they've got plates and screws, they will have bones that ache, or they'll have general malaise. People who have metal poisoning, as a matter of fact, I know people who have metal poisoning, like mercury poisoning and lead poisoning, even using a cell phone because of the EMF, the magnetic fields and electric fields that are sending the pulses out to talk to the cell phone towers. Every time they use their cell phone, if they hold it in their hand for too long a period of time, they develop a rash, and so they have to stop using it. I've met people and talked to them about this kind of thing, and yes, it's a real thing. It's the same kind of thing. These people who are sensitive to getting an MRI, who can't. I know people who actually have pellets in their legs from gunshots, sadly. And they can't get MRIs, and they also get sensitive. They also feel itchy when there's a geomagnetic storm. So there really are things that occur medically that sensitive people have issues with. And there's a whole host of different things that cause that. Maybe at one point I'll do a class on it that really won't be a class per se. It'll be more maybe just a Q&A conversation, or we'll just talk about some of the medical research that's been done. And I can't, because I'm not one of the afflicted, I can't necessarily say yay or nay, but I can go over some of the research and talk about, and put it in plain language for you. And then talk about specifically how that relates to space weather in what the events are that cause it, and where they would be more prevalent. So I might do that at some point. I need to talk to Lourdes about that, and maybe a couple other people like Chris, to see whether something like that would be warranted and everybody would want it. But that's going to be after all these series are done. Okay, I think, guys, I'm getting tons of questions, and I appreciate these questions. But I am going to move on, because if I don't move on, we'll never get through this. What about alien implants? Cute. If the IMF polar angle is south, do we tend to have more of a geomagnetic activity due to crack? Oh my goodness, you're probably listening to Tony Phillips. Crack in the magnetic field. I hate that. This is not a crack, by the way. And sorry, I don't mean to be like super harping on that. That those aren't your words. I know that, and don't worry about it. Who said that? Ron. Don't worry, I'm not harping on you at all. I just prefer not to use the word crack, and I know Tony Phillips at spaceweather.com does it all the time, because it gives a wrong impression. Remember that movie from last time? This is a very dynamic system. There is no crack. There's no crack. This opens up, right? This layer opens up, the flux peels back, but then it reforms. Cracks don't heal, right? And this is a shell. This is it literally opens it up and folds it over, right? So you're peeling back layers. It doesn't like crack open like an egg. I just have a problem with that, because crack feels so irreversible, right? When you crack an egg, you can't put it back together. It's like Humpty Dumpty, right? You just can't do it. This is crack. If that's the case, this is cracking all the time, and then it's reforming and cracking and reforming. I mean, it's just silly. It's not really a crack. It's a ballet. So yeah, the magnetic field in the IMF direction matters quite a bit. Now, when you say the polar angle, are you talking about obviously north-south, but east and west makes a difference. And how east-west makes a difference has to do with the coupling on the current systems here. No. Here. See this? The green line here? Yeah. So when you get a strong BY in the magnetic field direction, that can give you aurora, because not only does it couple here, it also couples here. Crosstail current. So when you get a strong crosstail current, you actually are still getting a lot of energy into the Earth's magnetic system. So that's one thing I tell, and it's an advanced topic, is that you don't necessarily need a strong BZ if you have a strong BY, so in either direction, because you're still pumping a ton of energy in. So there are people who get kind of confused when they're really good at looking at satellite upstream monitors, and they look at the magnetic field upstream, and they see this tiny BZ component, and they're like, why are we getting such strong aurora? There should be no aurora. We're just barely any, and yet we're getting this, and it's like, no, to look at BY, it's like minus 20 nanotesla, or it's positive 20, it's like this massive component in the crosstail direction, and it still feeds the aurora. So that's why. But so yes, the angle does matter. But that's an advanced topic. Okay, So hopefully this didn't confuse you so dramatically, but it gives you a nice little update or a nice little preview of what's to come when we talk a bit more about the ionosphere. I won't go through this in huge detail in the ionosphere, but we will talk about some of the systems and how they couple. But let's get back more to near Earth space. Okay, so now that you have kind of a sense of how, I just realized I don't need this because I'm not listening to anybody. Why do I have this on? I could take this off. I'm so used to doing this for class, and I'm thinking, why do I need this? I'm not hearing questions from you. I'm reading them. So understanding how the current systems work, silly me. Understanding how the current systems work a little bit and how latitude is going to play into that, right? Magnetic latitude and L shell is going to play into that as we begin to look at these different current systems. I want to make sure that we understand what else, how these current systems where they're being formed, where they're actually formed, and where they're actually existing, how they directly affect, okay, and whatever is out there. And so we're going to talk about the main one, right, when it comes to energizing things and causing problems for things, and that's going to be the Earth radiation belts, right? And I'm sure you guys have always heard about these, how these radiation belts end up just slamming the Earth or the near Earth space assets. And it is true. The reason why we worry about the Earth's radiation belts has very little to do with how intense, how dense they are. There's actually very little density compared to, let's say, the ring current. There's very little density in the currents that the Earth's radiation belts creates. What matters, really, so that's one of the reasons why when I go back here, you don't see us talking about radiation belts. Where's the radiation belt current system, right? It's not here. Well, then why is the radiation belts, why do they make such a big, splash, so to speak? Why do we talk about them all the time? Why do satellite operators worry about them all the time? It's not because of the currents necessarily, because of the energy, okay? So the Earth's radiation belts don't have a lot of current, but they have a ton of energy. The particles in there are very, very energetic. What happens when you have particles that are very, very energetic, that are what we call relativistic? It's like a trapped radiation storm all the time, okay? These particles at these really, really high energies literally can slam, and sometimes to be so energetic, they can pass almost right through an entire spacecraft, okay? Now, the ones that we mainly have to worry about, at least far out, are the electrons, is the outer zone. And that's what you're looking at here. This is the outer zone of the Earth's radiation belts. As you can see, it's kind of a smear, right? The inner zone is much closer to Earth, and how you have probably interacted with the inner zone or heard of the inner zone is in something called the SAA, the South Atlantic Anomaly. It's like the Bermuda Triangle of the radiation belts. If those of you who actually know about the SAA, what that actually is just the underside of one edge of the inner zone. Okay. Now the inner zone is filled with mainly protons. The outer zone is filled with mainly electrons. Okay. But these are relativistic. These are high energy. They're moving. They want to be moving essentially at near the speed of light. But you'll see for a lot of reasons why they don't. And let me see, what am I talking about here? Did I cover all this? Okay, yeah. Belts are affected by solar phenomena such as solar storms and radiation storms. So when you have, and I'll show it in this movie here in a minute, when you have the radiation belts, they are sustaining. Okay, that's because the Earth's magnetic field. If I can grab my slinky, as we've talked about many times before, the Earth's magnetic field, right, is the slinky. Essentially, the heart of the Earth's magnetic field is essentially a slinky. And of course, anybody who knows Cern, right, if Earth is sitting in the middle right here, this thing wants to move on me. It's kind of a lopsided thing, but this is Earth right here in the middle. Then the slinky kind of looks like this. This is, and anybody who knows Cern or knows a particle accelerator knows that they look like this, right? The toroidal thing goes round and round and round. Okay. Well, that's the neat thing about the Earth's magnetic system, is that it actually makes this perfect particle accelerator. And that particle accelerator is what creates these radiation belts, okay, and sustains them. So these particles are jailed in this magnetic slinky that, with space weather events, ends up getting more energized. Excuse me as I take a drink of water. Gets more energized and is a better particle accelerator. The more energized and more compressed the Earth's magnetic field gets, the stronger it gets. The stronger it gets, the better accelerator it is. And so if you have particles from the ring current co-located with particles with this regime, what happens is that inside that particle accelerator, that is the Earth's magnetic field, you get ring current particles that get accelerated, right? And they get accelerated to higher and higher and higher energies. So you can actually feed particles into this system when there are space weather events happening. Now, particles also get fed into this system from solar energetic events. So the radiation storms, some of those particles can get trapped in the radiation belts as well. Okay. And what I'll do now is I'll go ahead and show this movie. Let me explain what it is that you're about to see. Remember L shell, right? Magnetospheric physicists always look at things in terms of L shell. So you're seeing here's Earth at zero L shell. You're looking at half of Earth. Okay, we're going to look at a meridional cut. So basically a cut just like you see here, cut right through. Okay. So that black circle is Earth, essentially. And you're seeing particles. What this is real data, but this data has been folded into a dipole field. It's been mapped into a dipole field based on L shell. Okay, so the satellite SAMPEX and the instrument is LICA, and it went through. I mean, SAMPEX is a great data set. It lasted 20 years, but SAMPEX sampled all these different L shells in and out, in and out. And so, granted, it didn't sample all of these regimes all at once, but when it took data, what the author did, which is Joe Mazer et al., what they did is that they took it and they mapped, and Mark Looper, who's a really good friend of mine as well, he's also on Twitter if you've ever talked to him, really savvy particle and instrument person. They took this data and they mapped it into L shells. Okay, so even though SAMPEX was just crossing through a particular point on an L shell, they said, okay, that entire L shell has that flux, that intensity of energetic particle. And by doing that, they're able to make a movie. And I think you'll see starts in 1998, and you'll see each data point is a day. You'll see this move up, 3, 4, 5, 6, and then you see the days of you see the year, and you see the days of the year advancing. And the reason why this is so instructive is because it actually shows how dynamic just one side, right? We're just showing one side of this, how dynamic the radiation belts are. Now imagine, of course, that what you're looking at, and I don't know if I can let's see if I can show it to you. I don't know if I can do this, but if this is if this is the slinky, right, this is the slinky here, and you're looking at the L shells. Okay, so you're looking at one L shell, right, which is the slinky, kind of like this, but the slinky itself is sticking out this way, straight out at you. I don't know if I can get it quite right. So you're looking down kind of in a sense the tube with Earth being on this side. Okay, so if I take that away, that's what you're looking at here, right? You're looking down the tube and so you have to imagine that not just this side, but this tube stretches all the way around like an accelerator, right? So you're looking at one lobe, which is this lobe here. You're looking at one lobe, but imagine it going all the way around in a tokamak kind of thing, okay, around Earth. And that gives you the ring that is the radiation belts. Okay, so stretch this all the way around, but we're just kind of looking through a cut. And let me play it. Oh, and also, just so you know, because I don't know if I mentioned it, you can see the inner zone here. You'll always see it. Red will be really intense fluxes, so a lot of particles. Yellow, you know, well, blues and greens are the lowest fluxes. Yellows and reds get really high fluxes, okay? So here's the inner zone. And the outer zone really should be out here between 5 and 6. As a matter of fact, geosynchronous orbit, as I've mentioned before, is 6.6, which is out here. So to be honest, geosynchronous orbit is just at the very outer edge of the outer zone. But if you can see, here are what look like three intensifications, right? And I don't know if you guys have ever seen in nature or every now and again a press release, but that's released saying, oh, there's a third radiation belt. Oh my gosh, it's the first time we've ever seen it. You can see three radiation belts right there. This is why I'm talking about there's no such thing as a slot. And then one other thing before I begin to play. If you see, oh, by the way, it will go white. Okay, white is the most intense. So after red, you see red here. If you see white, that's the most intense. It means saturated. And sometimes you'll see white coming in from outside and coming down. If you see that, if you see white coming like this, that is a solar radiation storm that's hitting. Okay, and you'll see it actually penetrate. And sometimes you'll see it penetrate to the point where it ends up helping sort of the inner zone, but it's usually a geomagnetic storm that ends up intensifying the inner zone. And this region takes a long time to calm down. So you'll notice when it gets white and big and intense, watch how long it takes, how many days it takes for it to calm down. This is why satellite operators hate geomagnetic storms. Okay, so here we go. Let me play it. Media not found. Oh, you pain in the tush. Hold on, I've got to find it. When did you do that to me? All right, first of all, I don't recall this thing not being able to play before. So are you going to let me pull it? No, why aren't you letting me? Boy, I'm sure having lots of problems today. Why aren't you letting me? Okay, there. Whew. Couldn't get the PowerPoint to leave me alone for a second. Let's see. Where are you? I'm going to try to just play it directly. Oh, you're not on this system. What are you talking about? You're not on the system. That's not good. Do I really not have it on the system? I have got to find it. That is so strange. Okay. I bet you I do have it on the system. I just don't. Give me a second. And I will. Change systems here because I know I have it here. And sorry about that, guys. And now one of my lights just went out too. Boy, I'm just having all sorts of problems today. Hold on. Let me turn this on. Other thing so that I can make sure that I can give you this. Don't you love real-time issues? Plug this in. Hold on. That shouldn't take too bad. There we go. Luckily, I had the same charts up on this one. Now let me just make sure. Yes, good. So Haha. Now if I could just figure out why my light went out. There we go. Very strange. I am having all sorts of weird stuff happening. Gremlins. Okay. Sorry about that pause. Okay, so hopefully we didn't lose our place here. What is the truth? She's working for NASA. Actually, no, I don't work for NASA. NASA doesn't like me very much sometimes because I give them bad news. I'm not afraid to tell NASA when they're doing stuff wrong. That is the nature of my job, actually. So, okay. So same movie. Whoop. Let me make sure I stand out of the way. Good. So now you're seeing it. Okay. So that's days running on the bottom. You can see it's running pretty fast. That's 1998. But look at this. So you see the inner zone, right? That's here, right? The outer zone is essentially here. Okay. Mapping, as you can see, it goes clear out to 6 Earth radii sometimes. And typically there are 2 radiation belts, right? The outer zone and the inner zone. Okay. Those are the red regions. Right? But look how dynamic this is. This is the region that they try to call the slot, where people say, oh, we can fly satellites here and we won't have a problem. Yeah, right. How often does that slot get changed? Quite a bit. Now, we're getting into solar maximum, this 2001. See all the white coming in from the outside? Those are solar radiation storms, okay? Look how dynamic this region is, okay? A lot of that is from the Earth's magnetic field pumping in and out. Imagine those L shells, right, wrapping around. They're being pushed, they're being pulled. There's sometimes the flux is being peeled back. And this is what happens to the radiation belts. But remember, the radiation belts are the parts that have the most energy. Look at this. This is 2003. This is when we had the Halloween storms. Look how long that lasted. Did you see that? I mean, it's unbelievable. Look, there's another big one. Oh, in 2004, we had another big one. That was a big SEP. Oh, there's another one. Bam. Oh, there's another one. Okay. Shows you how incredibly dynamic this region is. And so it's very difficult for satellite operators to try to fly in any one particular location and think that they're safe and think that the system is going to remain the same, because it's just not true. You know, the system changes. It's very dynamic. And remember, as I talked about before, I'm getting this ready to go back to this system. As I talked about before, the inner zone, these are protons. The outer zone, which you don't really see very much right now because it's been flushed. Remember, if you guys have ever seen me talk about my forecast sometimes that I talk about Leo, Mio, Geo, I will say, well, you had the outer zone and it got flushed. All those particles got flushed during that storm. That's because a lot of that flux got peeled back. It opened up, it changed the magnetic field, or you had a big crushing of the Earth's magnetic system, and it pushed all those L shells in, and particles that used to be jailed because the magnetic field just a second ago was right here, it suddenly got pushed in, and the particles go, whoa, what happened to the jail bars? Geez, we're free, and we take off. And so they leave. And that's what happened here. As you can see, the outer zone actually got flushed. Okay, but there's still trapped particles here and in the inner zone. Okay, so this is an extremely dynamic region. And we're talking both protons, which cause a certain type of upset, and then electrons, which are further out typically, and cause a different kind of upset. It's not simple. And it's so difficult in my daily life. It's been so difficult to try to train people who build satellites and fly them that space is not empty. As a matter of fact, it's an extremely dangerous place. It's extremely hostile. It's extremely dynamic. And if it were easy, anybody'd do it, right? This is why satellites fail so much, is because it's just not a simple regime. What? I am getting pinged. Where's my phone? Now I've lost my phone. Where's my phone? I hear it. I can't see it. Oh my goodness. There it is. Let me find out who is pinging me. If I've lost, have I lost something? No. Okay. I just wanted to make sure it wasn't one of you guys. telling me I had done something wrong. So good. Okay. Okay. So what we are going to talk about next is something really cool. We're talking about the radiation belts, right? And I talk about, you can see over the course of time how these fluxes go. But you might not understand, especially when we think about current systems. We drew those current systems in the fashion of this diagram, right? So you see the ring current here being drawn is just a simple purple line, okay? And it's all in the equator. But then we, and you just see these very simple distributions, right? And just rings and simple, everything's in the equator, everything's simple and all that kind of stuff. And we see that even here in this diagram as well, right? Everything's sitting very nicely. The particles are behaving themselves and they're all sitting in these little tiny rings and really well contained. But then I talk about the radiation belts and it's not a ring, right? I mean, it's not a simple equatorial thing. It's smeared out. Why are the particles smeared out at not just, you got all different L shells, granted, but you also have all different, on a single L shell, you have all different latitudes, all different angles, right? From high to low in this sense. Why isn't it just sitting right at the equator? Well, that has a lot to do with how particles propagate. And I'm going to switch back to my other. Because I've got these really nice diagrams and I want them to be big. Cool, huh? This has everything to do with how particles move in not just the Earth's radiation belts, but how they move in the Earth's magnetic system. Okay? Particle motion, as if the current systems aren't complicated enough, particle motion is even more complicated. Okay? Particle motion is extremely beautiful, and yet it's also, and it does make sense. There are ways I will clarify what this is, but it's also non-trivial. Okay, there are 3 different types of motion, essentially types of motion that we talk about in the magnetosphere. So anybody who ends up reading journal articles on this or anything like that, you will come across these types of particle motions all the time. Okay. They're called adiabatic invariants. And this, believe it or not, is showing all 3 of them. Okay. The first one is called gyromotion. And I'll stand on this side for a second. The first one is called gyromotion. And this happens just by looking at a particle around a magnetic field line. When you have a particle around a magnetic field, if it's a neutral particle, it doesn't see the magnetic field. But as soon as you have a particle that's charged, suddenly it sees the magnetic field, right? Because there's electric fields involved and it's charged. So you have an E&M, there's a force on it, okay? And what that force ends up doing is causing that particle to spiral around a magnetic field. Now, if the particle had no motion this way or this way, it would just sit there and spiral just around and around and around constantly. And if depending upon if it's charged one way or charged another way, it would go the other direction, okay? Or if the magnetic field is pointing one way or another way, that dictates which way the thing spirals. Now, if that particle then has, let me see, do I want to talk about this yet? Yeah, I'll talk about it a little bit. If that particle has any motion along that magnetic field direction, then that particle won't just spiral, it'll make a helix. Okay, and once again, I tell you, no plasma physicist should be without a slinky because it's so good for so many things. It's good for describing magnetic field directions and what magnetic fields do, but it's also good and solar storms and everything else, but it's also good for talking about particle motion because this is the path the particle makes around a magnetic field. Let's say the magnetic field is threading through this thing, right? So it's like a broom handle. If I wish I had a broom handle to stick through this. But the particle would then follow this path if the magnetic field is, sticking, grab a pen. I've used a pen before. Here's a magnetic field sticking through this thing, and the particle motion is like this. The less speed that particle has going up or down, the tighter the spiral. The more speed the particle has going up or down, the looser the spiral, right? So it'll spiral up really fast or spiral up really slowly, depending upon how much speed it has in what we call the parallel direction. The speed that it has going this direction dictates the width of that spiral. Okay, we call that the perpendicular direction. So the more speed it has perpendicular to the magnetic field, the bigger the spiral. The less speed it has, the tighter the spiral. It also depends upon what species it is. Electrons spiral much more tightly around magnetic field, so their spirals and coils are really tight. Protons much larger. Heavies, big charged heavies like, I don't know, plutonium. No, I'm just kidding. Oxygen. Let's say oxygen has even a larger spiral. Okay. And of course, the speed, again, the energy. So the more energetic the particle is, the bigger the spiral is because it's got more perpendicular speed, more perpendicular energy. Okay. But nonetheless, it's trapped. This is what I'm talking about when I talk about jails, right? The particles are jailed by the magnetic field because they have to spiral around it. So as that magnetic field moves and changes direction, so does that spiral. Okay. So the particle path will spiral and bend. See how slinkies are useful? So if I have a curved magnetic field, the particle spiral will look like this. Okay, it will curve just along that magnetic field and be jailed by it. So that is what we're looking at. And I probably should have had it at the bottom panel first. Well, we see them both. This is moving too fast, but you can see those spirals. See the spirals? Those are all particles spiraling around those magnetic field lines. So if you're looking at the radiation belts, right, this is what the particles are doing. This is why they're smeared out. They don't just sit in that cute little ring. It's still a ring, but it's not just a simple moving around in a circle. Okay, these particles are spiraling around the magnetic field. But if you notice, spiraling isn't the only thing they do, right? They are also doing something called bouncing. Do you notice how they bounce up and then down and then back up again and then down? You see them bouncing? Right. That is the second adiabatic invariant. Okay. We call it bounce motion. They bounce from pole to pole. See that? Okay. And how do they do that? Well, it's because most particles don't just have perpendicular motion. They don't just have perpendicular energy. They have energy, they have speed, velocity component along the magnetic field as well. So they don't just spiral, they helix, they coil, and they spiral up, and they follow that magnetic field as far as it allows it to take them, right? So if you look at these particles, like there was one here, I'll try to use this example here, right? Now my thing's over there. I use this example here. You can see that particle. Notice that when it comes up this field line, it comes up and then stops, right? And then starts going the other way. Why does that happen? Well, what ends up happening here is something called magnetic mirroring. Okay. As the magnetic field lines, if you recall with the L shells, as the magnetic field lines get closer and closer and closer to the Earth's surface, they get closer and closer and closer together. All those L shells, they're really spread out at the equator, right? These L shells are really spread out, like you can see up here even in the top panel, right? See those magnetic field lines. Look at the difference between this L shell and this L shell, and then this L shell over here, right? Really, really spread out. But as you move into the Earth's upper atmosphere, if I get my hand in the right place, look how tightly the lines are. Look how close they are together. Okay. All those L shells kind of converge into a very tight area. Well, what we know about magnetic field is that as those field lines converge, right, that's showing the strength building up. The closer magnetic field lines are together, that indicates how strong the field is. So closer together, stronger field. Further apart, weaker field. Okay. You also can get that from just like the fall off distance, right? The further you are away from the core, the generator of the Earth's magnetic shield, which is in the iron core, the further away you are, the weaker the magnetic field is. So it makes sense that closer to the Earth's surface, closer to the Earth's core, it's going to be stronger magnetic field. Makes sense. But this is a nice way of doing it, depicting it pictorially. and it's consistent, right? So what happens with the magnetic mirroring is that these particles that have a certain amount of energy, as you notice, as they get closer and closer and closer to the Earth's surface, the spirals get tighter and tighter and tighter. Well, what's happening? The particles are slowing down, right? That magnetic field direction is the speed they have along that magnetic field direction is getting slower and smaller and smaller and smaller. And at this point, right here, the magnetic mirror point, that magnetic field it's actually exerting a force that's slowing down those particles, and basically a stop sign hit. It reaches a stop sign, and these particles cannot break through that. At that point, they mirror, and the force that's on them forces them to go the other direction. So it decelerates the particles until they stop, and then it forces them to go the opposite way. So all that energy, it's kind of like, like a tennis match. Pop. The magnetic field goes boop and hits that ball back the other direction. So then the particles then pick up speed up to the equator. And so they're at their highest speed when they get to the equator. And then they start doing the same thing. They start coming into the magnetic field to the pole on the south end. And the same thing happens. The southern hemisphere magnetic field goes boop and hits them with a tennis racket and hits that ball back. And so the particles stop, they get hit, they start moving back the other direction. They come back up the equator, they pick up speed, they get to their max speed, vertically, parallel speed at the equator, and then they go up to the northern hemisphere and they begin to slow down again because the magnetic field is slowing them down. So it slows them down and they get to that mirror point and they turn around and go back the other direction. So they're constantly bouncing from one mirror point to the next. Boom, boom, boom. This is part of that ballet that mathematically is actually quite simple. It's one of the adiabatic invariants. Okay, it's a very pretty mathematical expression for this. But these are the forces that the magnetic field places on these particles, and it has to very much to do with the dipole field. The shape of the field causes the particles to do this. This is also why fusion is so difficult. It's very hard to keep these particles contained, especially when they get very energetic, because they want to escape, and the shape of the magnetic field is so critical in how the forces play on these particles and what direction it makes them go. So, I wouldn't want to be a fusion physicist either, because that's just a nightmare trying to keep those particles contained. But as you can see, the Earth's dipole field does it in a very particular way. Now, we're still not done. There's one more adiabatic invariant. Okay, so now particles gyrate, and now they bounce. Okay, and that smears them out over all sorts of latitudes along a single L shell. Okay, along a single L shell, because they're following a single magnetic field line. They're jailed by that L shell. They're jailed in that magnetic field, but they are bouncing. Okay, so just because they're confined doesn't mean they don't get to walk the perimeter, so to speak. But there's one more thing they do, and that's called drift. Okay, in the Earth's magnetic field, because of the shape of it, there's yet one more force that's on them, and that force causes them to meander along the edge, the same L shell, causes them to meander across that shell. This is why it's so important for you to understand L shells are shells. They're not single lines. You would think from this diagram that these particles can only be on this line and they can't jump to another line. Well, if that line is the same L shell, yes, they can, because it's a shell. It's not a line. It's a shell, right? It's if you have to look at it in lines, imagine lines being drawn so close together that instead of seeing in discrete lines, now you're just seeing, one full thing, one layer of an onion. And that's what happens, is that these particles actually end up getting pushed along that onion layer, and they move in particular directions. Electrons move, if you're looking at the night side of Earth, which you're seeing here in this top diagram, right? You're looking at I'm assuming it's the night side, because the Earth isn't lit up, so I'm assuming the night side. If you're looking at it from the night side, that means dawn is over here. No, sorry. I'm looking at the mirror. Let's not look at the mirror. I'll get myself mixed up. If this is the night side, dawn is over here, right? And dusk is over there. Okay, because the sun is in the plane of the page, right? Electrons will always travel, if you're looking at midnight, if you're looking at the night side, electrons will always travel toward dawn, okay? And so they will go from this system, they will go in a counterclockwise fashion, okay, as looked at from the northern. If you look down on them from the North Pole, you will see a counterclockwise movement of electrons. Now, electron spiral, and of course that's what you're looking at here. You're looking at, see that yellow? That is a particle, that is an electron, okay, that is moving counterclockwise, as you can see. And I can't slow the thing down, I wish I could, but what you're actually looking at, if you notice, if you look closely enough, you can actually see it's actually a particle that's undergoing spiral, it's undergoing gyro motion, it's also undergoing bounce motion. It's just the whole thing is lit up all at once. And so it's showing that particular particle's path as it runs through all three adiabatic invariants. Now, electrons do it a certain way, right? They spiral a certain way and they move counterclockwise. Protons spiral the other way and they move clockwise in this system. So they would move the opposite of this electron. They would spiral and they would move clockwise because they're charged positively as opposed to charged negatively. Plus, a proton also has a bigger gyro radius. That's what we call the cylinder, the particle motion, okay, the helix that it creates. The radius of that is called a gyro radius. Protons have bigger gyro radii compared to electrons because they're more massive, harder to turn. It's like the difference between that motorcycle and the semi-truck that you've heard me talk about so much. Motorcycles can accelerate, can bend and get off the line faster, and they can also change direction more readily because they're not as heavy, right? Motorcycles are much faster, much lighter on their feet, so to speak, compared to protons. Protons are the big semi-truck. And then heavy ions are even bigger semi-trucks. They're like freight trains, really hard to slow down, really hard to turn, right? Same kind of thing out in space. So electrons can turn on a dime. They'll have tighter gyro radii. They can drift faster and more easily, and compared to protons and heavies. So protons have a bigger gyro radius, and heavies have even bigger gyro radius, and they can't drift as quickly. They can't move as quickly. This is why current is very much dominated by electrons as opposed to protons, even though the current carriers being electrons always means that the current is labeled backwards, because we always talk about proton. We always talk about positive charge carriers. It always frustrates me. Anyway, so with this, let me see what else I needed to I'm looking at my bullet points here. So when we talk about these adiabatic invariants, when we talk about jailbreak during a space weather storm, or any type of inclement space weather, or just even a reconfiguration of the Earth's magnetic system, jailbreak means one or multiple of these adiabatic invariants are broken. So the only way that can happen is if the Earth's magnetic field changes faster than the particles can respond. In other words, snap the fingers, magnetic fields can move that quick. Particles actually have to move. They actually have to, they got to hit the accelerator and go. Even motorcycles, even electrons take a little time to respond. Magnetic fields have no mass. They can change in almost instantaneously, relatively speaking. And therefore, you can break these adiabatic invariants. So the jailbreaks can be broken. And how they break? Backwards. The first one breaks will be drift. The next one that breaks will be bounce. Gyro motion, real hard to break, but you can break it. Okay. So when we talk about jailbreak, typically in a storm in the radiation belts where the outer zone gets flushed, we're talking about drift. We break the outer zone invariant because now this L shell is gone. It's moved, and the particle goes, "Whoa, what happened to the shell? I'm no longer on this shell," and so it's on a different drift shell now. And that drift shell that it's on now, because it just moved to a different shell, that magnetic field it was on is gone, and now it's on this shell, and it's like, oh, okay. And this shell that it's on now, that it's being forced to drift on, is now potentially an open path, and so it can drift out and get shot out into near Earth space and away from the Earth's magnetic system. So that's typically the adiabatic invariant that breaks. It always is the one that breaks first, the drift shell, and then we can break bounce, and then we break gyro motion. Gyro motion breaks with electrons really hard to break because they've got such tight gyro radii. But studies of reconnection, when you talk about reconnecting magnetic field lines, that's when you can get that invariant breaking. And I am not an expert on that. That's microphysics, and it's stuff that, especially in the Earth's magnetic system, because I'm not a magnetospheric physicist. That's a totally different PhD than what I have. So, if you want to know more about that kind of stuff, I could point you to papers if you're interested. But that's not something that I study. So, as you can see, the particle motion, even for things like radiation belts and obviously ring current, right, plasmasphere, all of the current systems that we talk about, they all follow this rule. Okay, the radiation belts are probably the most interesting simply because they're the most energetic of particles, and they're the ones that cause damage for satellites. But as you can imagine, as we start talking about getting into satellite orbits, right, and the types of things that they see, you're not safe, right? I mean, the radiation belts are in a lot of places. So just because you fly at a higher inclination, as we call it, satellite inclination, you're not sitting at the equator, you're not going to get out of that current system. You're not going to get out of that radiation belt, because you're going to go through what we call the horns of the radiation belt, which are these areas here, both high and low. Okay. So you're not passing through the heart of them necessarily, but you're still passing through them. Even the ISS passes through them. Okay. And this applies for both the outer zone that we're seeing here and the inner zone, which you can kind of see a little bit here. Okay. So what do you guys think? Any questions on that, on this aspect? Bill James, you just found my channel. Thank you. I was wondering if you have a Patreon. Yes, Space Weather Woman. Yes, thank you. Thank you for asking. I do. So I appreciate that. Fantastic. Oh, good, Chris. Because that was the question I was going to ask. Is this clear as mud? I mean, are you completely lost? Please give me some feedback. Does any of this make sense? Or have I blown your mind and it's cool? I mean, could you imagine that not just the current systems in the Earth's magnetic system, but just even particle motion could possibly be this scrambled? Do you see why I call it the second chef? I mean, we're not even down to the ionosphere yet. We're just starting. And already any space weather phenomena that's interacting in this very complex ballet is getting scrambled beyond recognition. I mean, I wish I had an egg beater this good in my kitchen. I'm doing that part with chemistry right now, and it looks similar. Interesting. Sorry, here, still processing. Not lost at all. Vince, oh good, I'm so glad. Not lost. Thank you. Makes sense. Robert, thank you. Oh, good. Okay. So during a solar flare strong enough to reach the Earth's radiation belt, do the belts flex or absorb or repel the flare? No. First of all, we have to be careful. When we talk about a solar flare, that's not what's going to be affecting anything like radiation belts. If we talk about solar energetic particles, meaning the radiation storm, then yes, those particles get kind of absorbed. They penetrate through. They have to penetrate through this junk, and they find an L shell which they can no longer penetrate. Right? It's kind of the same thing as like magnetic mirroring, like we see here. They end up getting to a point where they can't penetrate any further. They may have a lot of energy, but only the most energetic stuff can penetrate really, really through, and that's a lot of times galactic cosmic rays, and even they have a hard time penetrating through to the inner zone, to the inner part of the radiation belts. And you saw that in that movie I played, that Lika Sampex movie. You saw the SEPs come in, the big radiation storms come in from the outside and penetrate down to about the inner zone, but not much further. They don't really get below, even sometimes there's arguments as whether or not they even reach L of 2, which is the real inner heart. This is why we're safe, and why astronauts on the ISS are reasonably safe from solar energetic particle events. But when they go to the moon, totally different story. I mean, Artemis, they're there's just a lot of stuff, and we can talk more about that in a bit. So with the solar flares are mainly by themselves. They're just electromagnetic light, right? So you're talking about X-rays clear down to radio waves. Those aren't going to affect the particle stuff. Now, if it launches a coronal mass ejection along with it, that then hits, causes a geomagnetic storm, hits the Earth, and then pumps its energy in. Yes, that changes everything. That causes jailbreak. That causes all sorts of dynamics, some of which I talked about last class. And we'll get, and some of it I've even talked about when we were talking about, in the C courses, for example, in that series when I was talking about solar phenomena. But it all affects how this Earth system change, what the magnetic field looks like. It peels back the flux and peels back the layers. It compresses the layers. It can do all sorts of things. And we can, when we talk about a little bit more about the effects on the ground and we get into some of the events, I can show a model of what happened with the Carrington event back in 1980 or back in 1859. That was actually modeled by using the same model that I showed last time. And you can actually watch how this flux, how the layers on the Earth's day side get peeled back almost clear down to where there's like nothing on the day side of the Earth's magnetosphere. And in that case, don't even think for a second that these radiation belts would survive. Maybe the inner zone survived, but the outer zone was stripped, completely gone, because there's no flux. There's no magnetic slinky on the day side, because all the layers were peeled back. All that flux was added to the tail, and you had nothing on the Earth's day side. So the outer zone was completely gone. As a matter of fact, any satellite back in 1859, that would have sat out there would have actually been sampling pristine solar wind, and they would have been safe. Really, people say, "Oh no, the Carrington event with satellites." Carrington event, unless there's a radiation storm that can take it out. If there's no radiation storm, which is unlikely, there probably is one. But if it were just the coronal mass ejection, just the interplanetary coronal mass ejection hitting Earth, that dramatically changed the Earth system so much. Any satellite that's sitting out at geosynchronous orbit, it'd be sampling a pristine solar wind. It wouldn't bother it at all. Maybe a few of its instruments might not work quite right because they weren't really designed for it to be out in the solar wind, but they'd have a great time because, to be honest, they wouldn't have to deal with the Earth's radiation belts. They wouldn't have to deal with a lot of the dynamics and a lot of the particles that are shoved in this system. Because this could be a disaster during a Carrington event. So, or during a smaller event, let's say, this can be a real pain for those satellites. But during the Carrington event, if all this stuff is stripped away, they're like, yeah, this is great. But then you have to deal with a radiation storm, which is likely happening, and that'll just destroy it anyway. But it's a different phenomena. So hopefully that answers that question. Okay, so the ionosphere is a sink. It's a sink for the Earth's magnetic system. It's a source when it comes to lighting up, potentially feeding stuff into the neutral atmosphere, right, and creating more currents and conductivity. Increasing the conductivity of the layers. So it can be a sink, a source, but it depends upon what it is you're actually talking about. But for the magnetosphere, it's a sink. Let's see what other questions too. Okay, I see Bob Dole. I see number 2. I missed number 1, so sorry about that. So you might want to put that back. Does the core spinning alone generate overall magnetic field that settles into? Does the core spinning alone generate an overall magnetic field that then settles into L shells? Yes, the core spinning, meaning not the particles here, but the core in the Earth. The iron core is where it's all generated. And yes, the spinning of the core is part of that process. It also has to do with the Earth's iron core being a slurry right now. It's partially solid and partially liquid. It's like a slush, an iron slush. And we're finding that that's critical in how the dynamo is created. And it's actually quite complicated, but it's beyond the scope of this course. But it also explains why Venus doesn't have a magnetic field, and neither does Mars right now, because Venus is still completely liquid and Mars is completely solid. And we are at a very unique part of our history where the magnetic field is sustained this way. So hopefully that answers that question. I think I got it. Let's peel this onion further. Good. I'm so glad. Why not send people with no thyroid to the moon? Yes, very cheeky. Cute. I don't believe global got... I don't understand that you're saying. I don't believe global got hacked, but with hit energy from the sun. Oh, I don't know. Okay, guys. So complex. Thank you, Mary. Appreciate that. So complex, you make it simple. I'm glad. I'm so glad you guys are understanding this, because this is not... Anybody who can get this is... You guys are good, right? Because this is not simple. And hopefully I have blown... hopefully yes, we've got a Goldilocks core. Very good, wild alchemical spirit. Very, very true. This is not simple, right? And if you can understand this dynamic, then you are understanding a lot more about the Earth's magnetic system, especially in near Earth space, than a lot of people who work in it, believe it or not. Because there are a lot of people who really just think space is a vacuum, right? And I could just kill Hollywood and Stanley Kubrick and Arthur C. Clarke for generating that concept ages and ages ago with 2001 Space Odyssey. This isn't a vacuum, not at all. It's a very hostile and very busy place, and there's a lot going on all the time. So, okay, good. It sounds like everybody is understanding this. Yeah, and we have to talk about the core at some other time, okay? So instabilities in particle populations cause waves. You can imagine with all this stuff going on, okay, good, I've got the right one. With all this stuff going on, that nothing, not one part of the Earth's magnetic system looks like another part, right? I mean, you sample something here and it's very different than what is happening over here. Then it's very different than what's happening over here. It's very different than what's happening over here. And so when you have that much difference, that kind of dynamic, the first thing it tells a physicist is, uh-oh, waves. Because what everything always tries to do, entropy always tries to make everything homogeneous. It always tries to isotropize everything, right? You clean a room and 20 minutes later, it's a mess again. And you're like, how the hell did that happen? Well, entropy, right? You try to order things and keep this in its little compartment and that over here in its own little thing and this over here, and everything is separate and very different, right? And very well organized. And nature comes in and just like a big blower goes and just tries to blow it apart. How that works in near Earth space is through waves, wave growth. Okay. So as you have, and I'll show multiple versions of this diagram, as you have all these different particle populations doing all of these different things, you will also have a ton of different waves. Now, if you recall back in the C course, I believe it was the C course. No, it wasn't. It was in the solar flare. I think I called those the F course series. I think I called those the F series. That's the solar flare and radio bursts. In that course series, I showed what radio bursts look like as they come from the sun all the way to Earth. And we looked at the radio bursts and we watched how they dropped in frequency as you got further and further out. And at one point I showed a plot that actually had what the radio bursts looked like, what the radio noise looked like once you entered the Earth's magnetic system. And I talked about kilometric radiation. I talked about how the frequencies are down in the kilohertz range, even down into hertz range, right? And I said, so it's extremely noisy, I said, in that. Well, we're here. This is it. Welcome to the birds. Welcome to the sonic, dissonance, the sonic library of the Earth's magnetic system. These are all the birds that chirp all throughout the system. And funny thing is, I actually have sounds, and maybe at some point I should play them for you. I don't think I have them in this presentation, but you can actually hear. We've actually taken some of these and made them, translated them into what an audio sound of the same frequency would sound like, and it's actually pretty cool. But these are electromagnetic waves, so they don't propagate like sound waves do, right? But they have the same frequency range. And so this would be, if these were sound waves, they in an atmosphere, they would sound, we would hear them, okay? But they're radio waves. So, but as you can see, here's the sun. I'm standing the right way, yeah. Here's the sun. See, the solar wind comes in this way, and you can kind of see this bubble, this kind of purplish bubble that's showing the Earth's magnetic system without all the magnetic field lines. But as you can see, you've got a ton of different pulsations that come, and you're actually looking down at the Earth from the North Pole, okay? So you're actually, this is the North Pole of the sun over here is what you're looking at down on. So the North Pole of the Earth over here, right? If I can get my hand in the right place. So, oh yeah, it even says North Pole, duh. So as a solar wind hits the Earth, you've got the radiation belts around the outside, right? You've got, of course, the whole magnetic system at the edges just kind of warbling, and you get a lot of what we call ULF waves out here. That's what the purple is showing. I believe it's showing ULF, PC5 pulsations, yeah, millihertz. But you have things like what we call EMIC, which is the green that's happening on the dusk side. These are mainly for protons. They're electromagnetic ion cyclotron waves, EMIC waves. And that's a particle process that is trying to dissipate and isotropize, homogenize, make even, bring up the entropy of the system, because we get a lot of particles, a lot of protons that gather on this side. That move to this side, because you're getting a lot of stuff shot up from the tail. Remember, we talk about the slingshot. So you get particles coming up the tail. And what did I say? With the way the particle motion works, electrons go to dawn, protons go to dusk, protons go to dusk. So you're going to have a lot of protons building up over here, right? Of course, they drift around, but you're going to have much more protons because they're just coming in. And so before they get smeared out, there's a much bigger distribution of them on this side. And same thing here. You're going to have on this side a lot more electrons. Okay, and we'll see that in a minute. So you have the ELF, the extremely low frequency, and the very low frequency waves that are the chorus waves, really pretty sounds. You get and then you get plasmaspheric hiss. You can actually see part of the plasmasphere when we talked about the plasmasphere. The plasmasphere actually has a little finger that comes out to the front of the Earth's magnetopause. And we'll talk about plasmaspheric hiss. I'll show you a plot that has that. But you can see there's all sorts of different types of stuff coming in. Here's another picture of it. This actually shows the hiss much better. So again, you have the ULF waves. Okay, let me explain the diagram, sorry. So the sun is, and the solar wind's coming down this way. You're looking down at the Earth from the North Pole here, right? So this is the same kind of diagram. Remember, I like to show diagrams from multiple different perspectives, multiple different artists, so that you get to feel it over and over again. So obviously the tail is that way, right? Particles that are coming in from the slingshot are being slingshotted from the tail. Electrons go this way, protons go this way, and then they drift around, right? Electrons go counterclockwise as viewed from the north, protons go clockwise as viewed from the north. Okay, so you have a big buildup of electrons on this side before they get smeared out, and you get a big buildup of protons on this side before they get smeared out. Okay, so you have different processes that are happening, right? So around the edge of the magnetosphere, you end up getting the ULF waves, and then you get, and all amateur radio operators would love that because you guys know what ULF waves are, and then you get chorus waves, mainly from electrons on the dawn side. Okay, you get EMIC waves right here in the blue from the protons, because they're trying to smear out the protons. That's what the waves are doing, right? The waves are sitting here just like the big gardener's blower, just blowing all the leaves, just spreading them like crazy. Get it out of here, get it out of here. These are the gardeners. I guess the waves are like the gardeners, the landscapers of the Earth's magnetosphere. That's kind of cool. I don't know, love me or hate me. I just, it is what it is. Hopefully that makes sense to you. I think that's kind of funny. Just thinking of people going up with their little lawn blowers and leaf blowers and just blowing the leaves. Particles are like the leaves that get blown all over the place. And then you get from the plasmasphere, from the core of the plasmasphere, look at this. You get something called magnetospheric hiss. And it actually has this plume that comes out. And this plume actually drags these particles up to the edge. I'm probably using the wrong word, drag. The particles up to the edge of the Earth's magnetopause and deposits them out. And we actually watch these things get shot out. So our upstream monitors actually see injections or ejections of particles coming out through the magnetopause. And we know that the plasma hiss is busy. So the plasma hiss blower is spraying the leaves and isotropizing things and getting them to break, in a sense, jailbreak, and getting them out of the Earth's magnetic system. And we will see this over and over again. And like I said, I have recordings of some of this stuff, because you can actually hear this in amateur radio. In certain radio antennas will actually pick this stuff up, especially when there's particle precipitations. Because think about it, not only are these particles, these leaf blowers, blowing all these leaves all around, right? Blowing all these particles in all sorts of places to try to smear out the distribution, but it's also, some of these particles are actually precipitating back down into the Earth's upper atmosphere. Okay, and they're going along magnetic field lines, and they're being shot down. So they're not just being shot out of the magnetic system, they're also being shot down into the upper atmosphere. Okay, what we call the loss cone. So I have another picture. Aha, one more picture. Again, looking down at the sun from the Earth from the North Pole. Obviously, here's the front of the Earth's magnetic system, right? The sun and solar wind coming from over here down. And you get to see it all again, okay? Here's chorus waves, and this time they're adding the word whistler. Whistler modes are great, and we can talk about what those sound like. And in this case, they're actually overlaying the drifts, okay? And they're calling them ring current drifts. And why do they call them ring current? The reason why they're calling it ring current drifts is the particles that come in. Okay, first of all, you have the ring current, right? We talked about the ring current. These are low energy particles. The particles that come in from the Earth's magnetic tail as well with that slingshot, those are not relativistic. Those are not radiation belt particles. They're lower energy particles. But the ring current ends up being the source to accelerate those particles to higher and higher and higher energies. And once they get to be really high energy, they're part of the radiation belt population. But there's only a few particles that make it that high, right? The main bulk of the particle distributions in the current system is the ring current, much lower energy, occupies the same space, just a lower energy. But again, in this case, the electrons drift to dawn, protons drift to dusk. And you can see the chorus on the dawn side. You can see the emic waves on the dusk side. You can see the plasmaspheric hiss, and this time they've mapped it clear out to the magnetopause. Get my hand in the right place, see how it's touching the magnetopause. That causes jailbreak. And then you get other stuff. They don't show the VLF waves in this one. But as you can see in this one, the nice thing that they have in this diagram is that you can actually say, it shows a drift path of relativistic electrons. Oops, I've got my hand totally in the wrong place. Sorry about that. Do you see that light blue line going around the Earth? And the reason why they would show that is to show you that it's co-located. All of these processes are happening in and among the particles of the ring current and in and among the particles of the radiation belts. And a lot of times, the chorus waves, for example, are scattering particles down into the loss cone that then precipitate and cause aurora. These particles also, sadly, affect astronauts, because these particles get dumped down into low L shell, and they can actually cause very fast bursts of radiation dose to these astronauts. And the astronauts are actually beginning to pay attention to that, because they're getting really short duration, high intensity bursts. And we don't really medically know very well how that affects astronauts. And we don't want to have that. That oftentimes happens during big space weather events, right? And it happens oftentimes on the declining, when the weather events are fading. where all of this instability has grown and gotten big, and now the waves, now the landscapers have to come in because all the undergrowth is grown out of, we've got to reshape it and trim it and clean it up, and we got to blow all the leaves, so to speak. And that's when these wave processes grow, and now they're dumping particles down into the ISS orbit, as the part, not really down to the ISS orbit, but really through it. So as the particle, as the ISS flies through that region, there's going to be an area in which they pass through a region that is going to be very high radiation dose, and very short, dose rate for a very short time. And they don't want to be having astronauts out on EVA, right, doing a spacewalk when that's happening, because it's not healthy. Obviously, it shortens the astronaut's life out in space. Okay, I think that's it for that one. So here's another diagram. I love this one because it actually talks about it a bit more. So here's an electron drift path. Hopefully you're getting the idea now. Here is Earth. We're looking down from the North Pole. The night side is actually white. Sorry about that, but that's just supposed to be shaded. Sadly, it shades it white because I've got the diagram is in black and white. So the sun is up here. The solar wind comes down, and this is what's neat. You get fluctuations. You get the ULF waves, basically with the magnetopause and the Earth's magnetic field undulating. Remember, we talked about it being springy. That's how you get the ULF waves. So it's moving in and out. Okay. Here's chorus waves, and this is what it looks like on a spectrogram, like a waterfall diagram for those of you who are radio amateurs. You're seeing frequency on this side. And you're seeing, I believe these are chorus waves. Are they kilohertz or are they hertz? I forget. So I think this is hertz. So as you're seeing, I mean, it's, might be kilohertz. I'm trying to remember. Sorry about that. But you can see how these, if you look at them in over time, because this is time moving on this side, flux is the intensity and the color, and then wait. Yeah, that's frequency. So what you're seeing over time are sounds that go, and the reason why it's called chorus, they oftentimes call it dawn chorus. The reason for that is because these particles, when you hear them, if you were to translate them into an audio sound, they sound like birds chirping in the morning. Now I'll go up. Unlike whistlers, which do the opposite. Here's plasmaspheric hiss, and that's happening post-noon, right? And remember, that's because we get this plume that comes out, right? This plume from the plasmasphere that goes up to just post-dawn magnetopause, and where you get all the escaping. And this is what it looks like. Anybody knows what white noise looks like? Yeah. It just kind of sounds like that. Okay. And that's over time. And now we stand on this side. Here's emic waves. Okay. Emic waves, I will not try to sound like them. They're an interesting sound. Not super musical, but not super non-musical. As you can tell, they definitely have a tone. It's not nearly as sweet as emic or as chorus or whistler waves are, but they're definitely as you can see by the spectrum, they're definitely distinguishable. You definitely know you definitely can identify them when you hear them. But they happen on the dusk side, right? Because they're dealing mainly with the ion population, the protons. And that's the magnetopause coming in out. Plus, yes, and of course, these are the big ones, right? And they're happening, as you can see, all the way around. So different leaf blowers for different species and different times, local times. So you can imagine if you're a spacecraft moving through these different local times, right? You're sensing, you're dealing with different phenomena all the time, right? So there really is no part of the near-Earth space environment that is the same. So when people fly low Earth orbits and they fly in particular orbits, they're going to be, depending upon where they are, they literally are going to be flying through different environments. And so one of the first things that a magnetospheric space weather person says when someone says, my satellite just had an upset or just had a problem, the first thing that a space weather person asks is, well, where is it? What's your orbit? What's your inclination? What's your, and a lot of the different orbit parameters that you want to know. And then you start asking specifics about what kind of spacecraft is it? Is it a spinner? Is it, what kind of payload, that kind of thing. But it's literally because the environment, near a space environment is so incredibly different depending upon where you are, both in local time and in L-shell. Okay, hopefully you guys, this is coming across much more clear than maybe you've ever known it to be, right? So there's a lot more transport processes. Remember, these when we talk about transport processes, these are the leaf blowers that are blowing these particles. That's a transport process, right? It's being blown. A leaf is being blown from here to there. That's transport. And the process by which it's being happening is being the leaf blower. In our case, the transport process, the mechanism by which it's happening, are waves of a particular frequency that are acting on a particular energy of and species of particle. That's the transport process. And the transport is taking those particles and moving them from one location to another, hopefully into a loss cone so that they get rid of them, or out past the magnetosphere, out into near Earth space as a way to dissipate and isotropize things. Okay, so not only do we have the main processes, but there are other processes that are taking place, other wave processes that are less popular, less well known, or less effective. Right, these are some of the ones that are the most effective. They have because there's all sorts of other pulsations that are out there, and a lot of them are irregular. They don't last very long. These are sustained. And there's a whole plethora of people that study this stuff from the ground, because you can use magnetometers and watch how the magnetic field wiggles and look at all these, PC2, 3, 4, PI1, 2. I mean, there's just a whole mess of them, and you can get a PhD on that. So just so you know. And again, it's activity, location, and energy dependent, right? Which processes happens and why. Yeah. And it happens over all time scales. So it's definitely not a stochastic process, but definitely nonlinear. It's not easy to tell in one sense or another. It's not just related to one variable or another. There's all sorts of different couplings that happen. And they happen from microscale or microsecond time scales to day-long time scales, depending upon the frequency. And so I'll pause there. Matter of fact, because we'll get into satellite orbit types, because we'll start talking about how satellites navigate this. So hopefully, is this clear? I hope everybody is in. Oh, good. This clears up a lot. Good. We're learning. Good. Yeah, radio reception changes at dawn and dusk throughout the day. And the 40-meter band is a good band that demonstrates this. Yes, and so interestingly enough, it really does depend what time of day you are, even in near Earth space. Now, it doesn't depend for the same reasons per se as it does in the ionosphere. The ionosphere is far more driven by EUV, right? The irradiance from the sun and that type of thing, and then the current systems that couple down into the ionosphere. But a lot of those same space weather processes that do drive things that affect the ionosphere, they also affect stuff in near Earth space. So just because it's near Earth space, just because everybody's told you it's a vacuum, doesn't mean it is. And it also doesn't mean that it isn't incredibly relevant to what we're doing out there, right? What the spacecraft have to deal with on a day-to-day basis. And so when people talk about, well, SDO has an outage, or this has an outage, or SOHO, or these, that, and the other, guys, the space environment is incredibly dynamic and incredibly difficult to deal with. And so when I hear a lot of conspiracy theorists talk about, why isn't this spacecraft working, or NASA's hiding data, or, it's clear they just shut off the spacecraft because they want to, because they don't want us to see the aliens that are, they're shaking hands with. It's like, no, we're dealing with this kind of stuff. We're dealing with really hostile environments that are changing dramatically, and we're still learning what the environment has to offer and how it can affect us. And everything out here is radioactive. I mean, everything is charged. Everything is a potential for short circuits and charging up of the spacecraft and causing radiation damage, and I mean it's just nonstop out here. So it's much more complicated than people would like to believe it is. But hopefully now you guys understand that. So, oh, good. Okay. Yep. Learning. Yep. Got it. I'm still with you, learning a lot. Good, JD. I appreciate that. Keep going. Everybody's laughing. Jerry, you said that, let's see, to Jefferson, the change of propagation of radio between day side and night side and transitions, dusk and dawn, is the result of ionospheric layers changing. Yes. Yes. And it does slowly. And we will see as we go into the I series of courses how that change is not like a light switch, right? Because the layers are at different heights, different altitudes. And those different altitudes see the sun set differently, right? It's just the same thing as when you're standing on the ground and the sun is already set for you, but you look up at the sky and you see an airplane flying over and they've still got sunlight. And you're like, wow, the sun hasn't set for them yet, has it? Because they're higher up. Same thing with the altitudes, with the layers of the ionosphere. The lower layers have the sun set first, and so they begin to diminish before the higher layers do, because the higher layers are still seeing the sun, and so they're still getting ionized. So the gray line ends up not being, and the day-night transition ends up not being a very quick transition, but rather a slow one. And it's a function of altitude. Interesting, huh? And that has all sorts of crazy stuff when it comes to wreaking havoc on ionization. But yes, Jerry, so thank you for that answer. That was excellent. Okay, hams are radioactive too. Yes, I didn't learn that term until I actually became radioactive, and I started laughing. You should have seen me the first time I heard that. I was like, oh my Lord, that is so funny. The different fields have different meanings for different things, and I felt it very cool. I love that phrase. Well, now that they're disclosing UFOs, maybe we can finally get past all that. Oh my goodness, no kidding. We'll see. The sad thing is that governments don't like to admit what they don't know. It's like, well, I can't let you know that I don't know that, and I don't know the answer to that. So, that's part of the problem. But yeah, as far as I tell you, if there's any hostile, well, not hostile, if there are aliens out there and they have the technology they have, I mean, they look at us like, like a joke. They're probably here just, like watching a show, like eating popcorn and watching us because we're like, hey, yeah, like a little baby in a sandbox, they're just watching the kid fall down and, get dust and get sand in their eyes. That's probably what we look like to them. So they're probably just enjoying watching us grow and make a mess of our world. I don't know. That's what I'd do if I were that technologically advanced. I go, yeah, remember that? I read about that in our history books. Yeah, these guys are just experiencing it now. Oh my goodness, we are a mess, aren't we? Okay. It is a very gradual and very surreal experience to listen to it. Oh, right. Are you talking about some of the propagation? You can actually hear this, and like I said, I don't think I have it. I will remember to insert that particular. Yeah, I don't have it in this. Let me see. Let me look at my other one. It might be worth pulling up because I know I have it in my other set. I may end up pulling it up later. I don't have it open in my other one, but I do. I have Dawn Chorus. I believe I have Hiss, and I definitely have Whistlers, because we haven't really talked about Whistler mode waves either. But let me get through a little bit more about space environment, and then we'll have a good place to pause. Okay, so let me talk a little bit more about satellite orbits, and I'm not going to spend much time on this because you guys can Google this. Okay, and this is just kind of giving you an idea of how space weather people, magnetospheric people, and how satellite designers oftentimes talk about satellite orbits. Okay, basically we talk about three different types, or three different ways of talking about an orbit. We talk about it by inclination. So for instance, an equatorial orbit, or an orbit that is low inclination, I'm going to look at my thing over here, is sitting essentially in the equator, low, right, essentially going around the equator of Earth. So that's what we call an equatorial orbit. Okay, and that would have a very low inclination, or a 0 degree inclination. We also have polar orbits, and that's basically 90 degrees, right? So a polar orbit is something, you know, if you have an inclination of 90 degrees or minus 90 or, you know, 89 or something like that, you're in a polar orbit. Okay, and there's all sorts of different types of polar orbits, sun synchronous, and all, you know, all sorts of things that go into things in more detail, but it probably not relevant for this class. And then you have an inclined, something that's inclined, right? A lot of orbits sit here like this, and it's inclined to some degree. And of course, you can go positive or negative. Once again, you can have orbits. When people talk about orbits that are like, let's say, inclined at a 45, okay, great. You can also have orbits that are inclined at 110, which means that you go past polar and flip over to the other side. And that can be also reduced, but it has everything to do with which direction. If you're prograde, retrograde, there's all sorts of different reasons why you would talk about an inclination less than 90 degrees or an inclination greater than 90 degrees. There's reasons for that. But so inclination is something that we talk about. Okay, so when I talk about a low inclination orbit, I'm meaning one that's closer to the equator. It's sitting in the equatorial plane and sampling the heart of the radiation belts. If I'm talking about something that's highly inclined, okay, then I'm talking about an orbit like this that's only passing through, let's say, the horns of the radiation belt, right? Because the radiation belts, right, are, you know, you've got the main bulk of them in the equatorial region. And if I do a loop like this, right, if you're sitting in the equatorial region, you can be dwelling in the radiation belts. But if you're at high inclination, then you're not dwelling in the heart of the radiation belts. You're just passing through the edges. So you'll pass through this edge, and then you'll pass through the other edge. And so you go in and out of them. You don't dwell in them, okay? But you do pass through them, okay? So you can talk about it that way. You can also talk about orbits in terms of shape, right? So a circular orbit, an elliptical orbit. We oftentimes talk about eccentricity, right? And that, so you can have a circular orbit that is high inclination, right? A 72-degree circular. And then you talk about how far out, you know, what is the radius of that orbit. Or you can have for instance, and these are oftentimes what we call low Earth orbits. If they're very low, the perigee is very low. Okay, they're not very far out from Earth. So a low Earth orbit is oftentimes circular, and is any inclination. You can have them all different types. A high Earth orbit, a typical high Earth orbit, and HEO, as we call them, are oftentimes like this. They're very, very elliptical. Okay, and the reason for that is that they are able to come to their closest approach, which is called the perigee, and then they go way out, right, way out here. And the neat thing about Kepler's laws, which is the laws of orbital motion, is that when you get out here, you move real slowly. Like, so you dwell, you spend a lot of time, and then when you come in, you get faster and faster and faster and faster, and then you whip around. It's also the thing about gravity assist. When you get a planetary gravity assist, when you whip around real fast, you shoot you back out, and then you come out and you slow down to the edge, and then you slowly. So a lot of satellites that like to stare, they need to be able to stare down at Earth and not move very fast, and look down at Earth and stare and, you know, for a long time, are in HEO orbits, because they can look and they're not moving. So it's kind of nice. So you'll see a lot of them with imagers will be on HEO orbits. And of course, HEO, once again, can be inclined, highly inclined, you know, polar, low inclination. There's all sorts of types. And then, of course, you can also talk about orbits by altitude, right? How far up is it, right? A lot of LEO orbits, they talk about, you know, 600 kilometers or 600 nautical miles or something like that. And you get, you know, that tells you a lot, especially with circular orbits. Even GEO orbits, which is a circular orbit, we talk about how far out it is. Okay, you don't really talk about altitude so much unless you're talking about apogee and perigee. Perigee for an elliptical orbit, perigee is the closest approach. Apogee is the furthest it goes from the Earth, right? So apogee would have a different number than perigee. In a circular orbit, apogee and perigee are the same, right? So hopefully that. So if you hear us talk about this, this is what we're talking about. Another way to talk about orbits, LEO, MEO, GEO. You've heard me say that if you ever watch the Tomorrow shows, and sometimes in Space Weather News, I will talk about Leo, Meo, Geo. You also have a geosynchronous orbit, which is close to geostationary, not exactly the same, but you know, I'm not going to. I'm just giving you a range here. So low Earth orbit. Let's talk a little bit about that. Anywhere from about 160 to about 2,000 kilometers up. 160 really isn't. You can't really fly at 160 kilometers. Your spacecraft really has to be around 400 to 500 kilometers to even survive, even the low CubeSats, because there's just too much drag. But this is considered altitude for an orbit. But I kind of laugh when I see the 160. And then I could talk about this orbital speed. It's not really, it's here just for your reference. But low Earth orbit is where the ISS is. It's also how you end up, the low Earth orbits are where you end up running into the South Atlantic anomaly. And that's from and we'll talk about that in the next class. That's where you end up getting, you graze the inner part of the inner zone. Then you go out to medium Earth orbit. It's a lot further out, about 2,000 kilometers to essentially near Geo. And the satellite speed across the sky is a little bit slower. Orbital period can be, you know, you can get 2 to 24 hours ish, give or take an ish, depending upon what you're talking about. And then, yeah, you can talk about examples. I forgot, I should have told you. Example of Leo, of course, is ISS, Iridium, Globe Star. You know, a lot of the constellations. You know, Starlink, of course, is a low Earth orbit satellite system. MEO, classic one, is GPS, right? Sadly, when you're talking about Leo or MEO, you're now talking about L shells of around 3 to 5, right? Which sadly means it's sitting pretty much in the heart of the outer zone. So this is a very intense medium Earth orbits. MEO orbits are very, very intense because they're dwelling, especially low inclination satellites, are dwelling in the heart of the radiation belts. And then you get out to the geosynchronous, like I said, geostationary and geosynchronous, slightly different. But you know where they are. That's where you can actually stare at the same, you're rotating along with the Earth. You're staring at exactly the same location. You can have 0 degrees. You can have inclined orbits that are you know, that allow you to have that stationary point that you're staring at. So again, just for your reference, and there's a ton of geo birds out there, right? I mean, I think Sirius XM is now geo. They've been geo for a while. So is SDO, for example. SDO is geo. You know, most communication satellites are geo. It makes it very, very easy to communicate with the United States or whatever country of origin if you're just staring at it all the time. The problem is you have a slightly slower communication time. It takes like half a second for a signal to get down and back, which makes it not so great for internet. That's why you get a lot of times DirecTV or Starlink or a lot of these other constellations wanting to go to low Earth orbit. MEO at least, but definitely down closer than GEO, because the latency times really reduce. You can actually get faster latencies than fiber optic if you are in low Earth orbit. That's great, except, you know, we have to worry about satellite health and safety. Here is another plot, and this is mainly more for my Millersville people, but this is I did find this one on the web. It's nice because it actually shows to a great degree what the real scale size is. That it's a little bit compressed here, and I'm not expecting you to read any of this stuff, but it's a little compressed here to show you the difference between low Earth orbit, and then, which is in blue, really close, and then MEO, which is in green, and then GEO, which is out here in red. But it's still compressed because in actuality, you can see it down here. Here's really where Leo is, all the way over here. See it? That's Leo. MEO is this small area. Okay. Is that right? Yeah. And then HEO. Okay, so you can see how far away from Earth we actually do have satellites. And this is the nice thing I like about it too. Here's the moon. So when I talked about earlier, here's the moon. That's how far away it is. When I talked about earlier, remember we've gone through the whole thing about how far, how dynamic the Earth's environment is, right? And when you get like solar radiation storms coming in and smashing into Earth, or penetrating Earth's magnetic shield, the ISS, this is where all our human understanding is, right here. This little tiny region of space right here. And you saw how dynamic the region of space is, right? Now we plan to colonize the moon. Do you think we're ready? Do you think we understand the radiation environment? Do you think we understand what it's like to have long-term humans out on the moon? Now, granted, we had the Apollo missions, right? We got very lucky because there were several radiation storms that occurred. We missed them. Okay, they did not occur while we were there. They occurred in between. Okay, so none of the radiation storms that were dangerous, really dangerous, did any of the astronauts experience. But if we plan to colonize the moon, now have long-term bases in the Artemis program on the moon, there's no way, and we're going to do this during solar maximum, there is no way we're going to miss all the radiation storms like we did in Apollo. We're going to hit them now. But this is the experience we have. Do you see why the Space Radiation Analysis Group, the SRAG at Johnson Space Center, is a little bit nervous? They know very well what they don't know. Okay. So this is a huge, huge thing going on right now with Artemis, because there's a lot of radiation people going, oh my gosh, we really need to try to get a handle on this. And they know they can't shield it. And the astronauts know. The astronauts know that they are risking their lives when they go out to the moon to build these bases, because there's no way you can shield the astronauts as well as they need to be. And even in the shielding areas that they're going to have, these little bunkers that they have for them, they're like little water walls. You can't stand behind a water wall or be encased in a water coffin for 4 days, 3 days. Who could do that, right? You'd psychologically lose your mind. So I really don't know what the solution is for that. Basically, the astronauts are going to take doses. They're going to take bigger doses. They're probably going to have very short lifespans, so to speak, career lifespans out here. And I hope they get paid a lot because they're risking a lot. All right, and I'll do this last little bit here before we adjourn for the day. This was something you guys get to see. This is kind of cute because I did this originally many years ago, almost a decade ago, for the board of trustees at my company. I made this diagram, and it's long since been released. So, but Sally Ride, the last public talk she got to hear was, because I saw her about a month before she passed, was this space weather tutorial I gave. And so what I was trying to do, they'd asked me to kind of give an overview of what space weather is, so that people would understand it a bit better. And so I made this diagram. You guys already recognize this. This is the near-Earth system, right? And we've got all these different orbits on. And now you kind of understand a little bit more about what a geosynchronous orbit is, what a GPS orbit might look like, what a low Earth orbit might look like, and what a HEO orbit looks like, high Earth orbit, right? And I got a cute little sun over here with a little coronal mass ejection coming out just for fun. And then on this side, okay, I've got the same kind of idea, but instead of being mapped in the magnetic system, it's now mapped in just a linear system that goes up by altitude. Okay, this, don't worry about this. This is just spread out just to give you a sense of the layers. Okay, so when we're in near or really low altitude, the neutral atmosphere, that's where you see, right, the blue of the neutral environment. See the blue, right? And then as you go a little bit higher, you get to that yellow, which is the charged particles, right? And that's about where low Earth orbit is. And I put a dashed line. So low altitude, okay? Now it's just a regime, right? So it's supposed to be very simple. But as you move out, meaning up in altitude, you start getting into this dark blue region, which is getting into the zones, into the radiation belts, into where all those particles are bouncing and gyrating and drifting, right? And you start getting into that blue. Well, this is where the MEO orbits are, okay? And then you get into the heart of the radiation belts, which is here, the pink. And then as you move beyond them, you get out to, geosynchronous. You get out to the edge of the radiation belts, and you're further out. And that's where the geosynchronous orbit is. I put another dotted line to give you just kind of a guide of your eye. But here's the thing. If I put a little orbit or a little satellite, and we're going to have this satellite going in HEO, you'll see very, very quickly that as it goes around its orbit track, depending upon the type of orbit it is, it's going to sample maybe a little bit, like the geosync samples almost the same kind of environment all the time. A low Earth orbit samples the same kind of environment all the time. But certain orbits sample everything. So as I play this, I'm going to stand out of the way. Watch that little satellite on both sides. See how it samples? See how it goes through these different regimes? Yeah, I'm done in a sec. Okay, whoops. And that's what I wanted to show. And I think this explains it quite well. That when you're a satellite designer, depending upon where you are, whether you're sitting at geosynchronous and you're just sampling the outer edge of the outer zone, it's very different than sampling, let's say from a HEO orbit, all through the radiation belts and back out again. You go all the way down into the neutral atmosphere almost. Well, not in the neutral, but down into the charged atmosphere, almost to collisional. Okay. And so you're dealing with this. So down here, you're dealing with drag, you're dealing with oxygen, you're dealing with, all sorts of different types of effects that don't affect, let's say, the GPS orbits. But if you're in a GPS orbit, then you're sampling the radiation belts. You're almost constantly in the radiation belts. So GPS orbit goes from basically the edge of the outer zone into the outer edge of the inner part of the zone. So it's just sampling through it all the time. Okay. So that's the whole reason why a space weather physicist that works in the magnetosphere says, as soon as they get to a satellite designer who says, well, I've had an anomaly, they say, well, where's your satellite? What kind of orbit is it in? What's its inclination? Where is it? What does it do? And then they start asking details about the spacecraft body, because we have to understand what environment it is, right? And all that is very, very complicated when you look at it in the magnetic system, because it's all wrapped around itself. But it's kind of easy when you look at it here. But hopefully that gives you an idea of how complicated things can get. And then next time, because I've got to get off, my husband just came in and said, you got to get off. Next time we will talk about all the different satellite event effects and things like that, all the types of things that you can have happen to your satellite depending upon which environment you're in. Okay, and then we'll get into some real examples. I'll talk about all sorts of little things that happen and show you real data of how satellites degrade over time. So hopefully you guys enjoyed this. I am not going to have time, sadly, for a long Q&A. I usually do a big Q&A afterwards, but I just wanted to get through this to at least the stopping point. And I did a lot of Q&A in the middle of the class too this time. So hopefully that's okay with everybody, because it's been almost 3 hours, I believe, 2 hours and 42 minutes. So yeah. So hopefully this all makes sense to everybody. I'm looking into the chat right now to see what you guys think. Yeah. Does the GPS go up and down too? Well, they do, because their orbits, I'm not sure if the GPS orbits are exactly circular. They may be slightly the eccentricity may not be exactly what one. So it's I don't know off the top of my head. I'm not sure if they're circular, but they're in different planes, and they do sample different parts. And remember, the Earth's magnetic field, which we'll talk about later, the Earth's magnetic shield tilts a little bit. So even if they are perfectly circular, they're not going to be sampling exactly the same thing, because the symmetry of the Earth's magnetic shield is off compared to the geographic thing, compared to the geographic coordinate system. So thank you. Oh, good. I'm so glad you guys, learned a lot. Yes, this stuff is really intense. Some people, the funny thing is, in my Millersville class, the people who were learning about the second chef, they thought they did the solar phenomena, and that was what was going to be the hard stuff. And then I show them this, and they're like, my God, this is even harder. And I'm like, yes, it is. The second chef is actually far more complicated. And it's not that it's far more complicated in a way that is harder to understand necessarily. It's far more complicated in a non-intuitive way. At least the stuff coming off the sun makes sense that it comes off the way it does. in the Earth's magnetic system, you're bombarded by stuff that was just like, whoa, I had no idea that it was doing this kind of thing. So I know I didn't get a chance to answer a few questions for my Patreon folks. There's some questions about Earth effects down on the ground and current systems and how strong are they, things like that. I will address them more on Patreon, probably in written word, and we'll figure out another way to address them. But we really will. I'll really start talking about them in far more detail as we get to the ground effects, which is a little ways off yet. But I have to kind of teach the classes the way, from top down. Otherwise, we end up you don't end up in understanding what is happening in the Earth's ionosphere and down on the ground unless you know what's going on, what's driving all that, right? Because it is being driven from the top down. So hopefully you understand the method to the madness here, and this is why I'm teaching it the way I'm teaching it. Okay. Thank you, Nick. I appreciate that. Oh, good. You always learn something new. I'm so glad. I'll have to binge watch this one. Pretty thick stuff. Yeah, this is intense. This stuff is intense. Luckily, it gets a little bit easier, I think, in the ionosphere. But the magnetospheric part is really tough because you have to deal with a magnetic coordinate system that really affects particles in very unique ways. So, okay. My notebook is filling up really fast. Oh, good. And, if you're a Patreon member and any of this is confusing, obviously talk to me, tell me, and I will address it in the next class. And I might even address it online on Patreon. We might do like a supplemental or something where I can just sit there and do a Q&A. Or if people would prefer, I could actually pause in this and just do a straight Q&A where all we do is just go back and review all of these concepts because they are tough. They are tough. So keep that in mind and put comments. Let me know either in the chat, let me know on YouTube, and definitely my Patreon folks. Tell me in the comments in the post and all that stuff, and we'll figure out how best to deal with it because I really want you to be able to understand this stuff, and it's really fascinating, and that's why I'm taking my time with it. Okay, so all right, guys, have a wonderful day, and you're welcome. You're welcome. Thank you. I see a lot of thank yous, and I'm hoping everybody is understanding this stuff pretty well. Okay. All right, guys, I will have to sign off, and then I will talk to you soon. Okay, bye. Hi.